We don't have the second volunteer yet, so okay, are you ready? Okay. Hi everyone, thanks for coming. So our first speaker is Rishikesh, and yeah, floor is yours.
Okay. Hello everyone. Welcome to this talk on FO Complete Program Verification for heap logics. This is joint work with Aditya Murli from the University of Wisconsin-Madison and Aaron Conselman and P. Madhusudan from the University of Illinois Urbana-Champaign. So let's begin. We are interested in proving properties about programs that can destructively modify a heap. In this setting, we would like to prove Hoare triples of the form pre-prog post, which says that if we begin at a state with the heap as described by the precondition and run the program, then the heap gets transformed into a new heap that satisfies the post condition. For instance, the precondition here says that the original heap can be split into two disjoint lists pointed to by x and y. If the program is run, this heap gets converted into a new one such that the resulting heap is a list whose head is ret and whose keys are the union of the keys of the original two lists. However, expressive heap logics are inevitably incomplete. Checking the validity of triples is not only undecidable, but not even recursively enumerable. That is, there is no procedure that, given a valid formula, will terminate and say valid. And there are several reasons why heap logics are incomplete. One, many heap logics are defined over only finite heaplets. Second is quantified combinations of theories. Third, they use second-order quantification. For instance, to talk about disjointness, one might write, there exists two disjoint heaplets where each one is a list. Finally, data structures are defined recursively using least fixed point semantics. Our goal is to build complete procedures. In this work, we design logics to address the sources of incompleteness in various ways. One, note that first-order logic is complete over arbitrary models. However, even if we restrict ourselves to finite models, even it already becomes incomplete. As such, our logics will be over arbitrary heaplets, that is both finite and infinite. Second, we only allow quantification over heap locations. Third, we use unique heaplets to avoid second-order quantification. Finally, and unfortunately, the incompleteness due to least fixed points is not negotiable. Even the simplest extension of first-order logic with a least fixed point operator is already incomplete. Despite this, we would like to have some theoretical guarantee for completeness, and the guarantee we use is called FO completeness. The idea here is to ask for a complete procedure when recursive definitions are interpreted as any fixed point instead of just the least fixed point. Let's quickly look at the difference between least fixed points and fixed points. A list defined over least fixed point semantics would intuitively be locations that can reach nil via a bunch of next pointers. When interpreting it over fixed point semantics, it's simply some function constrained by the definition on the right. In particular, an infinite chain where x1 points to x2 and so on, where list of xi holds for every xi will satisfy the fixed point definition, but not the least fixed point definition. So by this abstraction, we are expanding the set of models that can satisfy a formula. Now, FO completeness is desirable for several reasons. First, if a formula is valid for fixed point semantics, then it's in particular valid for least fixed point semantics. Second, if the original logic is first-order logic plus least fixed points, then the abstracted logic is just first-order logic again, which is complete. This is nice because many automated reasoning tools we have are first-order, and FO completeness makes statements amenable to reasoning using such solvers. In fact, it's been shown that several practically efficient techniques that unfold recursive definitions are FO complete. And this leads us to the goal of our work, which is, can we design heap logics with recursive definitions that have FO complete and practically efficient verification procedures? And the answer is yes. The first logic we look at is frame logic, which was introduced by Murli et al. In 2023. This is a first-order logic with implicit heaplets that can be converted into first-order logic with least fixed points. We provide verification condition generation, reducing this to FO plus least fixed points for a frame logic fragment for which thrifty unfolding of recursive definitions is FO complete. Second, we define a new separation logic, SLFL. Separation logic was introduced by O'Hearn et al. A long time back. Such logics are typically second order, but ours has an alternate semantics that makes it translatable to first order logic plus least fixed points via frame logic. Let's look at frame logic. The key design decision here is to have heaplets be determined by the formulas. The heaplet of a formula is computed via a support operator. Intuitively, the support of a formula are the locations one needs to dereference to evaluate its truthhood. For instance, the support of a list will be exactly the locations in said list. And this has several nice properties. Firstly, it avoids second-order quantification. Since heaplets are captured by support, we can say two lists are disjoint if the intersection of their supports is empty. Second, it's been shown that frame logic readily converts into first-order logic with least fixed points. Furthermore, by restricting to only one-way functions, that is, functions can go from the heap to a background sort, but not the other way around, we obtain a fragment of frame logic for which we can do a thrifty unfolding of recursive definitions. And this technique is FO complete. And we'll be working with this fragment. The frame logic verification pipeline is as follows. We take a program annotated in frame logic, and it generates verification conditions in first order logic. This is then sent to a natural proof solver, which does quantifier instantiation and unfolds recursive definitions to prove validity. This mechanism is complete for first order logic, even with background theories, if we restrict it to a one-way fragment, as shown by Loading et al. In 2018. And we use inductive lemmas to bridge the gap between fixed points and least fixed points. As for the VC generation itself, we use a strongest post style method to generate VCs. We step through the program, track the program transformation and accessible memory. We collect frame rules and information about the heap. And of course, we need to make sure all of these fall into the correct fragment. And when designing a VC generator, we also have to take care of memory safety during dereferences and ensure that function calls access only the implicit heaplets defined by its precondition. For this, we use a relaxed post condition, which relaxes the heap condition by simply asserting that the heaplet of the precondition of the call is contained in the allocated memory, as opposed to it being equal. Function calls pose other issues as well. When handling function calls, the contract of the call tells us that the heap described by the precondition is transformed to one that satisfies the post condition. And using this info, we can have the portion of the heap that the call modifies. And we also have to generate frame rules reasoning about the recursive definitions whose supports are not changed. And if the support is unchanged, then the recursive definition will also remain unchanged. And these last two also introduces quantifiers, which have to be instantiated in a succinct way. We do this by tracking a set of relevant locations as we generate the VC and instantiate quantifiers only on these. We now move on to our separation logic, SLFL. Recall that a source of incompleteness of separation logics is the use of second-order quantification over heaps. A formula list x star list y is defined as there exists two portions of the heap such that list x in H1, list y in H2, and the two heaplets H1 and H2 are disjoint. And to avoid this, we introduce a new separation logic, SLFL, which is inspired by frame logic. Just like frame logic, we require unique heaplets That is, formulas hold in at most one heaplet, which avoids the existential quantification mentioned earlier. This is captured using supports, which is similar to supports in frame logic, which capture the locations in a heap that are relevant to the formula. The semantics differ from typical separation logic to obtain unique heaplets. For instance, true is satisfied if the heap is empty instead of being true for all heaps. Disjunction simply asks the heap to be the union of the supports of the two formulas, A and B, instead of saying that the entire heap is either the support of A or that the entire heap is the support of B. And these choices allow us to translate SLFL to frame logic. We have incorporated an SLFL to FL translator into our VC generation tool. SLFL annotated programs are converted to FL, and this is followed by the usual VC generation pipeline. We've tested our verification tool on a suite of benchmarks annotated in both frame logic and SLFL. We noticed that frame logic is faster across the board, and the translation from SLFL to frame logic incurs some bloat, but all benchmarks go through in reasonable time, in less than a minute. To conclude, we identified two heap logics, frame logic and SLFL, with recursive definitions with an FO complete and practically efficient verification procedure. We use FO completeness as a new yardstick for heap logics, from having no guarantees because logics are inherently incomplete to having some guarantees. This ensures verification methods don't resort to just heuristics that may fail even though they have simple proofs. In our case, any theorem valid in fixed point semantics will be proven. And in fact, many solvers already use a thrifty unfolding technique we use in our approach. I think time is up, right? For future work, that's it. I can talk about it more offline if you want. Yes.
So our second speaker, please come. And if you have any question, we may have time for one question. Or Francesca, you can come, and Mike.
I'll be here.
Could you please just come and check the mic, and we are gonna move on to the second speaker. Yes.
talk about guarding the privacy of label-only access to neural network classifiers via IDP verification. Okay, so neural networks are very successful but also prone to privacy leakage attacks. In privacy leakage attacks, the attacker extracts sensitive information about the training set. For example, the membership inference attack, at which the attacker tried to infer if an item was part of the training set or not. Other attack is the reconstruction attack, where the attacker tried to reconstruct an item from the training set. Okay, so to cope with these attacks, differential privacy was employed. In differential privacy, it's a popular criteria which addresses the question of how to analyze data while preserving privacy. Typically, we have a data analyst which can access a data set using a mechanism A. And differential privacy says that to make A private, we should add randomness. Formally, A satisfies epsilon differential privacy if for all data set D and D tag differing in one element, the probability to get an output O by applying A on D is similar to the probability to get an output O by applying A on D tag. This means that one item should not change the output of A. Now, differential privacy was employed in neural networks using DPSGD, and the idea was in the training itself, we want to add noise to the weights and biases to make the network private. The problem with that is that could degrade the classifier utility significantly. And now we ask the question, how can we preserve privacy while maintaining utility? This brings us to IDP, individual differential privacy. It's a property that was proposed by Jordi Soria. It suggests a balance between privacy and utility. It maintains the same structure as differential privacy, and it considers a given data set such that it provides privacy guarantees only for a given data set. In contrast to differential privacy, that provides guarantee over any data set. Here we focus on a given data set, and it's suitable to neural networks because in neural networks we have a given data set. Okay, so formally, given a data set D, a mechanism A is epsilon IDP if for each data set D tag that differs from D by a single item, the probability to get an output O by applying A on D is similar to the probability to get an output O by applying A on D tag. D is given, D tag differ by one item, and we do not expect one item to change the output of the mechanism A if it's private. Okay, so how can we apply IDP in neural networks? This brings us to our goal. We want to develop an IDP mechanism to preserve privacy and to maintain the classifier utility. Before that, let's try to understand, can train a classifier, for example, this orange classifier, using the full training set. Similarly, we can do another training set, D tag, which have the whole training set of D except from one item, the first item, and train the blue classifier. After that, we can compare the results of the orange classifier with the blue classifier. If the results are similar, this means that the orange classifier do not remember a lot about the first item. He saw the first item, but he still classifies like classifier that does not saw the first item. If they are significantly different, this means that it remembers a lot about the first item and can leak privacy. So this way, we can preserve privacy. We do that for the other item, the third item, the fourth item, and compare outputs. Okay, so how we can implement that? Here I present two naive approaches. We can go for brute force approach. We have the classifier that was trained using the whole training set. We have classifiers that were trained using missing one training item. And each time we have an inference and X, we can pass it through all the classifiers, check outputs, compare them, and if there's difference, we can add noise to make the mechanism private. Another option is to adapt DPSGD to IDP. This means that in the training itself, we can add noise which is proportional to IDP, and to get privacy like that. The problem with the first option is high inference time. Each time we have an input, we now should pass it through many classifiers and not practical. The problem with the second approach is it will add eventually a lot of noise and affect the utility of our classifier. And now we ask the following question. Can we design an IDP preserving approach that minimizes inference time and noise? And this brings us to our key preservation. We observe that individual privacy leaks via inferences, but not all the inferences. And to understand that, let's consider the classifier here, the blue one. Each time we have an inference X, actually what we do, we access the weights and the biases of the network. But the weights and the biases are functions of the training set. So each time we access the network, we actually access the training set. But the question if all accesses, if all x's can leak privacy about the training set. So to understand that, let's consider the figure here. We have classification results of a classifier, a 2D classifier, classifying into two classes, class 0 and class 1, and we show the decision boundary as the black line in the middle. We add to this all the classification, the decision boundaries of other networks that were trained using the same training set except from one item, and show them in colored lines. And now let's consider the green input here, the x. If we look at it, it classified similarly over all the classifiers. It means that this input, this access, is non-leaking. We should not add noise to it to preserve the privacy. If we look at the white one, sometimes it classifies as 0, sometimes it classifies as 1. This input is leaking, and we should add noise when we classify it. So our idea is to define a bound. This bound starts from the decision boundaries of the classifier, the black classifiers, expand, and its goal is to bound all the leaking inputs. So eventually, each time we have a leaking input, we add noise. Each time we have a non-leaking input, we do not need to add noise. This way, we preserve privacy and we preserve utility. Okay, so we said that we want to define a bound starting from the decision boundaries. How we can do that? We use the well-known term of classification confidence. In a classification, we have typically an input x. We show it to the classifier. At the output, we have classification scores. Classification confidence says if x is classified as C, then the confidence is the score of x minus the score of the maximal other label. To visualize this, let's consider the figure here. At axis Z, we plot the classification confidence. At axis X and Y, we plot the input domain. We can see that at the decision boundaries, the confidence is 0, because at the decision boundaries, we do not classify. So our bound will start from confidence 0 and expand such that it captures the leaking inputs around the decision boundaries. Okay, so so this is how it will looks, our bound looks, and now let's define our property using the classification confidence. We say that we want to find the maximal classification confidence at which we could find a leaking input. This means the network that was trained using the full data set will classify to C, but at least one other network which was classified using the full data set except from one item will classify otherwise. And here, this is how we write our property. Okay, so now we define our property, and now let's see how we compute it. To compute it, we depend on formal verification, especially in MEAL, mixed integer linear programming. And we have our property here. We should encode it as MEAL. Now, here we can find our classification confidences for each network. This means that for each classification confidence, we should encode the full network. So we will eventually encode a lot of networks here as large as the training set size plus 1. And that would be problematic in MEAL, because MEAL assigns one continuous variable and one Boolean per neuron. Here we have a lot of neurons in our probability, and MEAL complexity is exponential in the number of Boolean variables. So a straightforward MEAL encoding is impractical. How we address that? Naively, we can, instead of encoding all the network as a single MEAL, we can compute a bound for each network. This means that we can compare at each time two networks, the original network who shows all the training set with one network who saw all the training set except from one, and compute a bound. We can do that for the first, for the second, for the third, for the fourth, compute bounds, and at the end get the largest bound because it bounds all the other bounds. This way, we reduce the Boolean numbers from a lot of networks into two networks. But also this approach is impractical because we will end up solving a lot of MEAL problems, as many as the size of the training set. And this way, it will take us a lot of time. So what we do, we propose to do hybrid networks combined with branch and bound. This is our solution. Okay. So now let's try to understand what do we mean by hybrid network. We say that instead of go and compare pair, we can go for all the blue networks here that was trained using the whole training set except from one item, and merge them into one hybrid network. Now the hybrid network defined by intervals. Each interval bounds the values of all the original networks. For example, we can look at the bias here. It goes from 0 to 0.3. And if we look at the biases in the original network, we have 0, 1, 0, 0, 1, 0, 3. So we bound all the values. And then what we just need to do is to compare the hybrid network with the original network, the orange one. We will get our bound, and we can see that the bound that we get is a little bit larger than the bound that we get when we solve precisely. And why is that? Because in hybrid network, because we are working with intervals, we add over approximation. For example, in this interval 0, 0, 3, we have a value of 0.2, of 0.2. But there is no bias in the original network with 0.2. So intervals does over approximation, and because of this over approximation, we get a sound but not precise bound. So what we do is branch and bound. We can go for the hybrid network and split it into smaller hybrid networks, and this goes on and on until we reach a precise bound. Okay. So now let's describe our approach. We call it Lucid. It accepts all the classifiers. We start from doing the hybrid network. We encode as meal. We submit the encoding to a solver, and the solver compute a bound. It retrieves a bound. We stick this bound with its hybrid network and push that into priority queue. Now after that, we can fetch the hybrid network with the maximal bound and check if its size is 1. If its size is 1, then we finish, because we have a bound, a hybrid network composed from network which can bound the rest. And then we could finish. Otherwise, we split it into smaller hybrid network and do other iteration. In inference, each time we have an X, we can compute its confidence and compare it to the bound. If it's smaller than the bound, then it's leaking. We should add noise. If it's larger than the bound, then it's not leaking. We do not need to add noise, and we can retrieve the classification as it. This way, we save privacy and we save utility. Okay, so now let's talk about our evaluation. We evaluate Lucid on several data sets. We compare it to naive approach and DBSGD-based approach. It achieves an inference time that is 156,000 times faster than the naive IDB. Its accuracy is 27x less degradation compared to the naive noise. If we compare it to the DBSG approach, it achieves 0 IDB with only 1.4 accuracy degradation. DBSG approach cannot reach 0 IDB, and it can reach 1.2 degradation compared to 12.7, which DBSG achieves. Of course, we pay in time. To compute the bounds, we need 4.8 hours, and to train a network for DBSGD, we need less than a minute. Okay, so now let's summarize. We address the problem of privacy leakage in neural network classifiers. We develop an IDB mechanism. We introduce the new concept of IDP-DB bound. We propose Lucid, which compute this bound and solve the privacy leakage. Lucid relies on meal, hybrid networks, and branch and bound techniques. It achieves better results when it compared to DBSGD approach and naive approach. So thank you for your attention and questions.
Any question, please come up. And next speaker, please come. Thank you. So yeah, while we are switching the gear. Oops, watch out. So about, so you mentioned this, degradation in the precision.
Yeah.
Right? So it depends on the applications, right?
It depends on what?
Oh, so something was with 27 times less precise, and the other was like 0 point something.
Yeah.
What makes that difference, you think?
The idea at the end is to keep the classification utility, the classifier utility, but the time is in computing the bounds, because it takes us time to compute the bounds. But that's what we do once and offline. Once we have the bounds, we can use them for any input. So there is a trade-off here. For example, the SGD do not need to compute offline bounds, they need to train a network. We do not train a network, we compute bounds.
Okay, thank you.
Thank you.
Okay, ready? We can take your time.
I'm ready.
Okay, then the next speaker is Robert.
Yes.
Okay.
All right. Cool. All right, hi. So my name's Rob. Today I'm going to talk about program alignment for relational verification. This is joint work with my co-authors Prasida Mukherjee and Benjamin Delaware. So when we talk about program verification, we're often looking at a single program execution, and we want to prove something about it. So here's a program that computes twice the square of its input, and we might want to ask, does it actually do that for all possible inputs? And there are lots of different tools that we have that can help us answer this question, which is great. But not every question that we have deals with only one program execution. We might have some that deal with multiple program executions, maybe multiple programs. Here's an updated version of double square that's, I guess you could say, optimized. It needs half the amount of loops to get to its result. And we might want to ask, do these two programs do the same thing? So these sort of like industrial strength verification tools for relational verification, which is what we call this case, are a little bit harder to come by, which is a shame because there are lots of interesting relational properties that we might care about. They come up in practical software development and verification all the time, and we would like ways to prove these properties. So even if there aren't these industrial strength tools, there are many approaches out there to doing relational verification. I'm going to sort of bucket them into two categories. The first one I'm going to call bespoke relational verification, where the idea is that you come up with some formalization, maybe it's a Hoare logic or maybe some language theoretic approach to representing the relational verification problem, and then you write tools that leverage that relational verification formalization, and those tools can rely on some powerful abstractions or mechanisms you came up with, which is great. But the problem is you have to write and maintain the tools, which in practice, many of us don't have the resources to put into, for example, Daphne or one of these larger tools. So the other approach I'm going to call a single program intermediate representation. The literature often calls this product programs. We found that this is a little bit of an overloaded term, and some things that fit in this first bucket are actually called product programs in the literature. So we call them intermediate representations, but product programs. So the idea here is that you have your multiple programs you're trying to prove something about. You combine them into a single program that maintains the semantics of running the two programs independently, and then you hand that single program off to single verification tooling. So the advantage here is that you can leverage these industrial strength verifiers sort of for free, but not really, because you have to produce combined programs that are useful to the verifiers. So what do I mean by useful? Well, let's go back to our example. We have these two programs we want to prove something about. I sort of have one with a green bar and one with an orange bar. And one thing we can do to come up with a single program that does the same thing as executing these independently is just sort of rename the variables and then put them one after the other. So I have the entire green program, then the entire orange program. And this is encoded for Daphne, so I can hand this off to Daphne and verify, which I can, but only if I give it this sort of complicated loop invariant. The loop invariant has to be very complete in terms of how it summarizes what the loop does, so that information sort of percolates down as we go on. So we can do a little bit better, so we don't have to have such a complicated invariant. We can sort of group subprograms that are similar together. So here's a version of this. You can see the green bars are intermixed with the orange bars, and crucially, I've merged the loop bodies together. So now I can have a loop invariant that reasons about what's happening sort of as the loop goes iteration by iteration, because the two loops were doing something similar. So I have this much simpler invariant now, which is great. Notice that I did have to duplicate a loop body to line up the iterations. Remember, one of these programs had a loop that iterated half as many times as the other. So to make this a sound, keep the semantics of the original program soundly, I have to sort of duplicate the loop body here. Okay, and this problem in general of putting subprograms into correspondence to make verification easier is called alignment, and it's tricky. You have to sometimes transform the programs by unrolling loops or duplicating loop bodies. If there are multiple loops in the programs, sometimes you have to figure out which loops correspond to which. And the existing approaches in this space of a solution here sort of rely on people to come up with those alignments. They're not really, there aren't automated approaches. So we asked, can we find these alignments automatically? And that's what this work is about. So we have an approach called Kestrel for doing that. There are three main pieces here. The first is we have an algebra of alignments that tells us, helps us understand sound ways that we can realign the program and still keep the semantics of the original two programs. We use a data structure called egraphs to represent the space of possible rewrites using these rules for alignments. And then we do a data-driven search to, once we have this representation, to find the best alignment that's represented in this egraph. So I'll sort of briefly go over these three pieces. The first is this algebra of alignments. This is inspired by work from Antonopoulos et al. From Popple 2023. And what we're going to do is we're going to have this notation that uses brackets to indicate when two subprograms are related. So here I have two subprograms A and B, and I put them in this bracket notation to indicate that they're related. I can have things that are single on the left, single on the right. I can sequence these related programs together. And I have control flows that appear at the algebra level. So here's a relational while that relates to loop conditions with two loop bodies. And then I have a set of rewrite rules that tells me how I can rewrite terms in this algebra in ways that preserves the semantics of the original program. So I don't really have time to go into detail on what those rewrite rules are, but I'll sort of try to give you a picture of what it looks like to use them. So we start out with our two programs here. We put them into this algebraic term, which is just the entire program on both sides of a bracket. And then we can start using the rewrite rules to regroup things, compose them together, lift whiles into relational whiles and things like this. And at any given time, we can take this algebraic term and sort of reify it back into our source language and get an aligned program that has the same semantics as executing the two programs independently would have had. Okay, so once we have this algebra and we have this rewrites, we want to know what are all the possible ways we can rewrite something so that we can start searching over it. So we use egraphs for this purpose. Egraphs are graph data structures that are designed to represent equivalence classes on terms under sets of rewrite rules. So perfect, that's exactly what we want to do. Each node in an egraph has a sort of a set of symbols that you can sort of choose. One symbol that's in each node and sort of pick that as your symbol to put into your AST or whatever, and then go down the branches and sort of do it recursively. So I'll give you just a brief example of what this looks like with an algebra that's maybe more familiar than the rewrite algebra. This is just Boolean algebra. So here I have an expression, and I have an egraph which represents it. This egraph, the dotted lines are the nodes, and then the solid lines are the choices inside of each node. And you can see I only have one choice in each node, so I can only extract one term out of this, which is the exact term that I have here. But if I apply a rewrite rule to this egraph, I get something that looks like this. It looks sort of similar, but note that now I have an E node here that has multiple choices. So I can either choose the not and then go down the branches, and I'll get back this original term that I have, or I can choose the and go down the branches, and I'll get this other term, not A and not B. And I can keep adding rewrite rules to the egraph, and the egraph relationships and choices will get bigger until at some point I'll hit some saturation where there aren't any more productive rewrite rules to add into the graph. And then my egraph is representing my space of possible rewrites. Okay, so we take our algebra of alignments. We use that in our egraphs to sort of saturate the egraph and figure out what all the possible alignments we could have are. And we sort of compactly represent that in an egraph. And now we need to figure out what is the best alignment that's hidden, that's somewhere in that egraph, right? So we do a data-driven search for this. So to extract a good alignment, we first have to figure out what is a good alignment. So the answer to this question is ultimately a good alignment is one that makes the backing single program verifier work. So it sort of depends on the backing verifier, but we can be sort of heuristic about this and say that there are certain things that make it easier to reason about. One of them is fusing related control flow structures. So in our example, remember fusing the while loops together made it easier to reason about. Also, making sure that when we have loops that we fuse together, that those loops, the iterations terminate at the same time. If they don't, you have to insert these runoff loops that run off the extra executions that didn't happen in the combined loop, which is hard to reason about for one of these single program verifiers. And note that these kinds of properties we care about, some of them are syntactic properties, some of them are semantic properties. So this sort of suggests that the analysis we need to do to figure out what a good alignment is will be some combination of syntactic and semantic analysis. So here's what we do. We start out with some baseline extraction from the egraph, which maximizes the number of fused control flow structures. And we use this as sort of a baseline. And then we can find sort of neighboring, close by alignments by sort of tweaking the choices we make in these e-nodes. So we can take one of our e-node choices and choose something different and get a closely related alignment. And then we can use MCMC to, like simulated annealing, for example, to sort of converge onto an ideal alignment. The cost function that we're going to optimize as we do that convergence will be a semantic cost function. It will be over the execution traces for these candidate alignments. And this is the way that we can judge whether or not we have a good semantic alignment. And the details here I don't have too much time to go into, but I will refer you to the papers for the detail of this MCMC process that we do here. At the end of the day, when we put it all together, we have something that looks like this. So above this dotted line are things that are happening in our source code language, like C is what we used. And then below the dotted line, we have things happening in the alignment algebra land. So we start out with our 2 source programs. We embed them into the alignment algebra, into some original unaligned term. We put that term into an egraph, saturate it with the rewrite rules from our algebra. Then we go into this data-driven loop where we find nearby alignments, run the aligned programs to come up with execution traces, and converge onto some alignment that seems ideal. Then we take that alignment that we found, we reify it back into the source code language again to get some aligned single program that we can then hand off to single program tools. So we tried, we used Seahorn for some of our evaluation. We used Daphne and Daikon for invariant inference for some of our others. This is what we found. So we took a bunch of benchmarks from the literature. We compared sort of the naive concatenative alignment with just the syntactic extraction from Kestrel, and then the full semantic pipeline from Kestrel as well. We found that Kestrel was able to align and verify all of our benchmarks within a minute, except for one that requires synthesizing a novel loop guard condition, and that's out of scope for what Kestrel currently does. We also had a suite of benchmarks that we found that used abstract data structures. So these have operations that we can formalize the semantics of and give that to the backing verifiers. We found that Kestrel was again able to align and verify all these programs within a minute, except for 2. One of them was this another one of these cases where we had to synthesize a novel loop condition, which is out of scope. And another one, we computed the alignment, but then our backing invariant inference generator was unable to generate a good invariance for it. Okay, so we also sort of looked at what is dominating runtimes as we do this verification. So the takeaway here is that for the smaller examples, the runtime's dominated by loop invariant inference. But as we get to these more complicated examples that require more semantic analysis, the simulated annealing starts to take over the runtime. So that's Kestrel. Just to summarize, we have lots of interesting relational program properties that we want to verify. One of our approaches for doing this is to construct these intermediate single program representations, but aligning them is hard. So we have an approach called Kestrel, which uses egraphs over an alignment algebra to find those alignments, and a data-driven search to find semantically desirable alignments. And we found that to be effective across a suite of benchmarks taken from the literature. The code is available on GitHub, and I'm happy to take questions. There you go.
Question, please.
Hi.
Hi.
Thanks for the presentation. My question is that can your algebra handling the programs contains some complex data structures?
So yeah, we have a suite of benchmarks that use that look at using abstract data types, which so we can do like lists and stacks and things like this. We have to axiomatize the operations on those data structures. So like we have to come up with axioms. What does it mean to have a stack and pop something off the head or whatever? So there are sort of well-known ways to do that. And we can put that axiomatization into our program, and then we sort of rely on the backing verifier to use it. So we do have benchmarks that do that, yeah.
I noticed that you are using the concrete trace. So what's the performance? I mean, every time you search the candidate program.
Yeah. So we have to be a little bit careful about how we do the execution so that we don't have loops that run for a long time and things like this. So we have to be smart about how we generate test cases. For our benchmarks, none of the programs were very large, so we're able to collect those execution traces fairly quickly. But as you get larger and larger programs, it could be the case that becomes a performance bottleneck to collect those execution traces.
Yeah. The abstract semantics of the program.
Yeah. Okay. So.
Just a very simple question. Can you just align 2 programs with the side effects, for example, memory operations?
So we ultimately rely on the backing single program verifiers to do the actual verification. So if those backing verifiers can reason about side effects, then we'll run execution traces and come up with what we think is a good alignment and hand it off to the verifier. So, but one of the advantages of this approach is that we get to leverage whatever the backing verifier can do. So if the backing verifier can handle effects, then we can produce alignments that maybe will work. Yeah.
Okay.
Yeah. Thanks.
Yes, so oftentimes loop alignments are not 1-to-1, it's maybe 1-to-2, or maybe 1-to-n, where the n depends on some condition on the variables. Mm-hmm. How much of this can you support?
So are you talking about like one-to-n programs or like?
No. So like you have like a slow and a fast algorithm, and then you need to align multiple.
Yeah. So in our example, we took like we had loops that were running at different rates, right? And we can one of the transformations that we look at is duplicating loop bodies to sort of put things into alignment that way. So yeah, we have. I didn't. You should see the paper for the rewrite rules that we have, but some of the things that we look at are doing those kinds of transformations to make things sort of line up.
Okay.
Yes.
Yeah.
Yeah.
Okay, thank you. Let's thank the speaker again.
Thanks.
And move on to Eric.
So hi everyone, I'm Eric, and today I'm going to present the work I've been doing with my collaborators at UCSD. So the name is Laurel Unblocking Automated Verification with Large Language Model. But before diving deep into what we did, I want to come back on why automated verification and why not like proof assistant, or like what are the differences and what does it exist. And so for that, I'm not going to use what I did, but mostly what was written in the Daphne paper, which is like there's like two ends of the spectrum. There's like on one side is like proof assistants with Lean, that like or like Coq that use tactics and that like a lot of manual efforts, and potentially you need to have a decent amount of knowledge in formal methods. And on the other side, there's Daphne that like offloads a lot of the proof to the SMT solver, but we stayed like kind of at the program level. And so for that, we have like the automation through SMT solver. But what Rustan didn't talk about is that now we have actually another kind of automation that is taking over. I don't know if you heard about it, but it's called AI. And so we kind of need to think about like how is this changing this paradigm? Like, is it making like, for example, theorem prover like easier to use than automated verifier? And how can we apply AI to both of this technology? And so today I'm going to focus on automatic verifiers and Daphne and how can we apply AI to it. But before that, we actually need to understand what's the automation that is already available in Daphne. And so for those who were at my talk yesterday, I had a user study where like people were complaining about Daphne or saying the good points about it, and they had this method here that was like, okay, I want to verify this method that applies a discount on the number X with a certain percentage, and I just want to show that my result will be positive because I don't want to have a negative price and lose money. So pretty important for them and pretty straightforward to implement, but somehow difficult to verify. And why? When we look at the code, it's straightforward, it looks correct. However, does it verify? It does not. Like Daphne tells you, like, yeah, I cannot verify that the result is positive. And so as I said yesterday, what you do is you add assertions to help the SMT solver and help Daphne and guide it towards like the goal that is proving that the result is positive. And so what you need here is this assertion that says like that the multiplication on two positive terms results in something positive. And so this is kind of surprising for a programmer that has no formal methods. But however, especially when we say, oh, it's automated, why do I need to add this assertion if it's automated? But for someone that knows formal method and actually read the paper that I referenced before on Daphne, well, Rustan was well aware of this. Automatic, this is not to say effortless. For it really usually requires interaction at the level of the program being analyzed. And so what's interesting here is like, well, Rustan, what he was saying is like, I will ask you maybe to add annotation or facts about things that are in the program. And indeed, like here in the assertion, we're talking about X and factors that are like a variable that we can see clearly in the program. So, okay, this is great, but users still complain about this. And now we have AI, so obviously we can do better, right? And so the idea is like, we can push this automation further by generating this assertion automatically. And so for the problem to work, for the solution to work, I want to make the problem simple. And so for this, I'm going to base myself on observation made on real-world code and on code base that are available online. And so the first one is assertions in Daphne are the most used annotation, 5 to 11% of line of code. Forget about loop invariance. They're a small part of the annotation. They're like less than 1%. Why? Because when you go like higher in your proof, you're not in imperative programming anymore, and hence you don't need loop invariance. The second thing is kind of like super intuitive. Well, you rarely start a proof from scratch. Yes, you're going to start it at some point, but your proof, like, you're going to have multiple steps, and so like these assertions, you might have to like you might have like some backlog proof that you already work on. And also like there are a ton of proof available that you can look at. And so now that we have a problem that is kind of simple, let's apply to an LLM to it and see if it actually works. And so like the question is like, can we fix this proof by inserting one assertion? So like we have a program like the one I presented before that just need one assertion, and we need to we ask the LLM to find it and see if it works. And so for this, we use this benchmark from actual real code that is deployed, like the standard library in Daphne, CDAR, there is a notation library, and Daphne AVMC, there is a random number generator. And I want to emphasize that this code is a non-trivial Daphne code. It is not like some like benchmark that is made up. It's like actually code that was written to be deployed. And so what we see in this graph is actually when we just ask this question and we ask to generate the assertion, we get a really low success rate, like less than 10%. And when we're a bit smarter, we say like, oh, look, we had an error message before. Can we just give it to the LLM? Well, we only get up to 15%. And well, if the LLM can generate like only 15% of the time the good assertion, well, nobody is going to use it, right? So good news, we still have some work to do. But what we can know now is like LLM do not work out of the box for assertion generation. So we need to actually be smarter about it. And so the question next is like, why don't they work? Why is it not working? And so here I have a lemma. You don't need to understand what this lemma does, and actually you can't because there's a bunch of dots. But what you can see is that there is an if and else case, and the assertion is needed in the else case. This is for showing termination and for helping the SMP to show termination, but the assertion is needed here and not in the if case. And so the question is, where does the LLM generate the assertion when you just ask it to add an assertion, right? Well, not really where we want. In the baseline case that I showed you, like it goes between like 0 and 15 lines far from where the assertion should be, and the error is a bit better, but still not great. And this is something kind of really precise, because if you offset by one line, you might be in a different path of your program, and the assertion might be useless. So okay, what we learn is like, unlike users, LLMs struggle to actually find the correct location for assertion. So, well, the solution seems simple. Can we help the LLM with the location? Well, we have the error message, and as and with like some kind of algorithm, we can actually provide a placeholder to tell, based on the error message, where should the assertion go. And so we can now provide a placeholder to allow the LLM to focus on the assertion. And what I mean by that is like now the LLM will actually not think of the token in terms of like both a placement where the assertion should go, but just like now the assertion should go there. These are the tokens and the assertion that will generate for this position instead of others. So we did this. How does it work? Well, it works pretty well. Like what we see is a 2-time improvement versus just giving the error message. And in this one, we don't even give the error message. We just give the placement and we ask to generate the assertion. So great. The second thing that is also great is that on the first try, we actually get 25%, which is good because LLM are actually quite expensive to run. But 25%, well, still not that usable. So can we actually do better? And as I said, we rarely start a proof from scratch. And missing assertions are likely to be similar to assertions that are already in the code base. And especially when we looked at Daphne code base and we actually clustered some assertions, we discovered that most assertions actually have a really similar structure. So there's only few types of assertion that we will write in the code base. They all like some kind of variation, but they all have the same structure. So the idea is like, then let's use this assertion that's already there, form similar lemmas, and provide them to the LLM, because LLMs are well known to work well with examples. And so how does it work? Well, we had the baseline that like around like over 30%. Now we had examples. And actually, we did one thing that was really interesting. We took example assertion from the same code base at random. So completely random, like I think it was like 6 different assertions from the same code base. And it actually works really well. So example assertion from the same code base are beneficial. And you might wonder why. Like random assertion would help. Like as I said, there's only so few type of assertion that actually exist in your code base. So meaning that even if you pick at random, there's a high chance that you will pick an assertion that is similar to the one you need. But we can be smarter. We can actually try to pick the assertion with some kind of similarity based on the context. So now we know that our lemma has a certain structure, like with the if and else like previously, and we know that we have another lemma that has the same structure. And we can use the assertion from this other lemma to, as an example for this new lemma. And that's what we did in the other line here in yellow. And what you see is we get some small improvements. So example assertion from similar contexts are actually better. And since like the similarity metrics now are like quite cheap, it's something that we should use. And finally, now we are above 50%, which I would say like if 1 time out of 2 an LLM can help me write the assertion, I think I would be pretty happy. But when does it fail? So here we have another lemma that like we need to generate this assertion here in fair array 2, and we provide an example. And if you look at the example, the structure is like really similar. And so we say like, okay, we're on good track, an example is similar. And what the LM generates is actually really close, but if you can spot the difference, it's 1 character away, is like, in this assertion is, in this code base is infer array 1 and infer array 2. And the LLM doesn't know that because we don't give it the function that are existing because there are too many functions existing. But now, we could think, and we didn't do that, but that's definitely something that could be improved, is like we could add some functions to the context depending on the first answer to LLM, or we could also try to do some program repair. The second example of when does it fail is this other lemma, and what you need to notice here is you see the word flatten everywhere. And if you know how LLM works in terms of probability and token, you will guess that every assertion that is generated uses flatten. But that's not what we want. We want this assertion that x plus ys is equal to ys. And so here, we need to understand, like, at some point, can we ban some element of the assertion to ask the LM to force the LM to go through a different path. So finally, we had this first thing of like providing the assertion placeholder to focus on the content of the assertion, then find similar assertion, and we made this into a tool that we call Laurel, and that we generate assertion. But I want to come back on one thing. I talked at first about program verifiers and the proof assistant and automatic verifiers and how AI will change this thing. And I promised that I will answer this. And actually, I lied because I'm not smart enough for that. So I asked my favorite assistant, ChatGPT, and he told me like a bunch of reasons of like what kind of research we should do and what kind of thing we should do. And this is all great. And actually, if you read it, it's not that bad. But what made me happy is that one part of it is, well, what we should do to apply AI to verification is to synthesize assertion. This is an important thing as the AI role. And that made me happy because that's a part of what we did. So thank you.
Thank you. Come in, any question?
Hi there. I was curious with the different models you tried. So I understand there are some LLMs that are fine-tuned for proof engineering. If you experimented with those, compare those to ChatGPT at all?
So this was used with ChatGPT at first 4 and then 4.0. We didn't try with fine-tuned models because at first when we did this, there was no fine-tuned model for Daphne per se. Like most of the ones were like for proof assistants. I think it would increase a bit the success rate, but it will not fundamentally change the problem. Like for example, 4 was not as good as 4.0, but we had the same thing of the location not being great and the example being quite useful. So yeah.
Thank you.
Oh, yeah. Thanks for the great talk. So did you use some kind of prompt techniques like chain of thought or something, right?
Yes. So a prompt was like really worked on, and like we also tried like chain of thoughts. If you try chain of thoughts, you get a bit better result, especially on the baseline. But like by adding just the location, you get significant improvement no matter what, with or without chain of thoughts.
Okay, thank you.
So to my understanding, your benchmark only contains those functions with fixed lemmas, and your job is to synthesize the assertions in the function, right?
Yes.
So why don't you focus on generating the lemmas instead of the assertions? I think this is more is a more difficult problem.
So I'm not exactly sure of the question, but I'm going to try to answer it to the best of my abilities. What we did is sort of ablation. We have a lemma that, or a method that like actually verifies. We remove one assertion, and if this assertion makes the proof fail, then we add it to a benchmark. So the goal for the LLM is to add the assertion that will make the lemma pass. So it is a simple task, but it is a task that needs to be done for the code to prove.
Okay.
Okay, thank you. Let's thank the speaker again and move on to Michael.
Hi everyone, I'm going to tell you about our work verifying instruction selectors in production compilers. The context of our work is compilation in security critical contexts. That might be a JavaScript or WebAssembly engine in a browser, or in the cloud and a function as a service platform. These environments use JIT compilation for performance and rely on sandboxing for security. But a compiler bug could be escalated by malicious code to allow sandbox escape and stealing data. So security depends on compiler correctness. Formal verification offers a solution, and CompCert has achieved a fully verified compiler. However, that was a great human effort. So the techniques aren't mainstream in compilers like Clang and GCC, and a focus of our work is how we can use formal verification selectively to improve the security of production compilers. Our work focuses on CraneLift, which is a compiler that backs the Wasm-Time WebAssembly runtime, and it's used and trusted by major companies. In addition, we focus our work on a particularly vulnerable stage of compilation, which is instruction selection, that bridges a compiler's IR down to target machine code instructions. This can be simple, where a single IR instruction maps to a single ISA instruction. But a lot of the complexity in production compilers comes from the fact that the selector performs a wide array of peephole optimizations, in which sequences of IR instructions are mapped down to selected ISA instructions. Not only that, but single IR instructions can contain a lot of embedded logic. For example, this signed division requires an entire sequence of instructions to do required overflow checks. And I'm sure you can see that there's a bug in this one. This one, we'll talk about later, wasn't security critical, but other bugs have been, where some of the worst vulnerabilities in Wasm-Time have caused critical CVEs, and the root cause was an instruction selection bug. We'll make this concrete later, but we'll think of instruction selection as a graph, where IR nodes enter on the left and are ultimately rewritten to ISA nodes. But crucially, this happens via a sequence of intermediates, which are governed by instruction selection rules. And prior work has taken the natural approach of verifying this rule by rule, where developers can handwrite specifications for the nodes, and the verifier can confirm that the edges preserve behavior. However, in production compilers, these graphs are huge. This is the graph for the ARM backend in CraneLift. And that brings us to our first challenge, which is that with prior approaches, we would need massive annotation and specification burden to reach full coverage. Not only that, but we don't just care about verifying pure computation. We also have to reason about side effects, because these instructions may load and store from memory, or they might trap in exceptional circumstances. And prior approaches have dealt with this by modeling the entire state of the machine and carrying around an entire representation of the memory array, for example, is bloated and causes inefficiencies at scale. Lastly, modern ISAs are huge, and instruction selectors target a significant subset of these instructions. We need to know their behavior, so we have to specify the semantics of many machine instructions with intricate behaviors. If you do this by hand, you're likely to get it wrong. So that brings us to our work in Arrival, which is an instruction selector verifier for CraneLift that allows end-to-end verification with high assurance and reduced effort. And we do this with a few techniques. We introduce rule chaining that allows us to reason about entire paths through this graph at once. We introduce a lightweight state modeling method, and we automatically derive our ISA specifications from vendor-provided semantics. And with all this, we're able to verify nearly all of this ARM backend required for compiling WebAssembly core instruction set. And we'll focus on a couple of these techniques with the rest in the paper. So let's take a look at how CraneLift achieves instruction selection. It manages complexity with a domain-specific language called ISLE, in which developers write rules consisting of a left-hand side pattern, and on a match, it will rewrite to an expression. So what we're looking at here is a match on IABs, or integer absolute value instructions, on types 32 bits or less. And on a match, it produces this ABS node on 32-bit operands with sign-extended inputs. But in fact, there's two rules, one for the 32-bit case, one for the 64-bit case, and they both use this same helper. So you can see how this graph begins to form. But in fact, it continues, because this ABS helper is implemented in terms of a compare immediate and a conditional negate, so the graph gets a layer deeper, but we're not done, because in fact, this compare immediate is implemented by emitting the lowest level machine code IR in the compiler. And we see the same on the bottom. So actually, even in quite a simple case, instruction selection is implemented by the interaction of multiple instruction selection rules. And as I said, prior work introduced a specification syntax that allows developers to define the behavior of each of these nodes and verify that the edges preserve behavior. So we could take that approach here, right? We could verify all the edges by specifying the behaviors of all the nodes. But that brings us back to our challenge of scaling to the full instruction selector. And that's the motivation for our rule chaining technique. The idea here is, what if we could reason about an entire path through this graph at once? And Arrival allows us to do this. It is able to compute the composed effect of all the rules along a path and verify that the entire composition preserves behavior. On top of that, we have an algorithm that can enumerate all viable paths through this graph. And this helps us achieve our goal of reducing specification burden, because developers are only required to provide specifications at the beginning and at the end. So that's the idea, but in practice, in these production graphs, there's complications, that there are cycles, which mean that in practice, there are infinitely many paths through the graph. There are also high-degree nodes, as well as common helper nodes, which might have a low degree but appear frequently, which means that if we apply this technique in an unlimited fashion, we would hit path explosion. So the insight of rule chaining is that we can gain most of the benefit by applying this technique within subgraphs. And Arrival provides control to the developer by placing intermediate specifications as well as annotations to control the use of rule chaining. And the result is that we can avoid specifications on most intermediate nodes while keeping this path explosion in check. So that's how we deal with intermediate nodes. We still have this challenge of specifying the behavior of all of the ISA instructions we're targeting. There are many of them, and they have intricate behaviors. And we handle it by auto-generating them. Thankfully, in recent years, processor vendors have begun to distribute machine-readable formal semantics of their ISAs. This was led by ARM, but we believe that Intel is following suit pretty soon. Doesn't this just solve our problem? The answer is not quite, that these semantics they distribute target many use cases, and as a result, they are very verbose, and they contain low-level details not required for user space or compiler verification, as well as all possible processor variants, which means that they are actually notoriously difficult to use. Thankfully, recent prior work, a project called ASLP, which actually featured in this conference already, solves this by partial evaluation. It is able to take a concrete instruction on the left and produce a succinct semantic program describing its behavior. However, we're still not quite done for the domain of compiler verification, because we don't actually have a single concrete program that we want to reason about. We need to reason about entire families of programs, Or more specifically, we need to know the behavior of this machine code IR, which itself covers millions of possible concrete instructions. So that is, we need specifications for symbolic machine code. The observation that we make in Arrival is that, in fact, fields of this IR map naturally to bit fields within the encoding. And we leverage this to build a pipeline for specification generation. Starting with a family of machine code IR instructions, we were able to represent this as sets of symbolic encodings, where each one has partially fixed bits and partially variable ones. On top of that, we forked and extended the ASLP project such that we can generate semantics for these symbolic encodings. And then, given such a semantic program, we can convert it into IL specifications to use in our verifier. And with that, we were able to auto-generate almost all of the ISA specifications that we needed for verification, replacing thousands of lines of code that would otherwise, or producing thousands of lines that would otherwise have to be written by hand. So with that, we were able to use our verifier to verify almost all of this ARM backend required for compiling the WebAssembly core instruction set, totaling over 6,000 rule chains. And doing so with reduced developer effort, where of all of the nodes that are encountered in this verification scope, 60% of them benefit from some form of Arrival's automation, be that terms that don't need specs at all because of chaining, or a large number of them that we're able to just auto-generate through this ISA specification pipeline. And it's viable for introduction into production workflows, where a continuous integration run of this verifier takes 11 minutes and covers almost all of the scope. And lastly, returning to this sign division bug from the beginning. This is a bug where an overflow should have been caught, but wasn't because of a miscompilation. Arrival is able to catch complex bugs like this, which required analyzing 12 IL rules in combination. It required modeling state, particularly traps and flags, and it required intricate specifications for 7 different ISA instruction families. So with that, I've presented our work on how we scaled verification to production instruction selectors, and thank you.
Thanks a lot. Any question? Yep.
Hi, thanks for the nice talk. Have you checked the soundness of your encoding of your semantics for those instructions? Like, did you find any bugs in your encoding? Because you are basically reinvented new semantics for all those instructions.
Do you mean, did we find any bugs in ARM's specification, or did we find?
No, you use this ASL to generate the semantic from the symbolic encoding of your instructions. So is that, how do you know that's the sound?
Okay, so we do have to trust that our translation is correct. We did find some bugs in the process. We found some bugs in Crane Left's assembler itself through this process. And we did find some bugs in the prior handwritten specs that we were using. Okay. But we do have to trust that the translator from ASL into our language is correct.
Okay. Have you dealt with any instructions that need to deal with concurrency? How complicated is that?
We haven't. So do you mean things like atomics? We haven't covered that. Yeah.
Okay.
Yeah.
Okay, next question.
Thank you for the good talk. In the CI slide, you mentioned you achieved 97% coverage or something.
Yeah.
I wondered if you can talk quickly about what's left. Is it timeouts, or is there some technical limitation?
Yeah, it's timeouts. So the verifier is SMT-based, and it struggles with all the things that SMT often struggles with. For example, large divisions, multipliers, and remainder operations, as well as some of the large population count instructions sometimes time out. So yeah, the things that aren't covered in that verification scope, they do get covered if you run it long enough. but we think there's value in the CI environment in covering most of it, right? Yeah.
Thank you. Please thank the speaker again. And now, last speaker of this session, Yeti.
Hello. Okay, the sound is okay. So, hi, okay. Hi everyone, I'm Yedi from National University of Singapore. So it's my pleasure to share this work. For today, the topic is about the verification of neural networks against the bit flip attack setting. So actually, the bit flip attack is already known as a type of fault injection attack for a long time, especially in the past. Such attack mainly appears in the hardware security issues, especially in the domain of cryptography algorithm trying to release some key information for the private key. So in this talk, I try to revisit such attack in the domain of neural networks from some verification perspective. So also this work is the first attempt to try to verify the absence of such attacks in the neural networks. Okay, so first I will quickly introduce what is the quantized neural network. So actually such quantized neural network is structurally very similar to the original deep neural network, and for the quantized here, means we trying to use a lower precision format to store and try to reduce the computation overheads in the runtime. So literally, there are many ways to define the quantization method. Here, I give one of the most simplest method, also very prevalent method named symmetric quantization scheme. So given a fixed quantization bitwise, so we first try to figure out what the size of the quantization step. Usually, such step is defined by the value range of the parameters of the target model, and then give floating point values and the obtain the quantization step from the previous computation, and we will obtain such quantized values in the integer domain and also in the fixed point number domain. So under such compression method, the model will be greatly compressed and can be efficiently deployed on the ad devices. Okay, so in recent years, the researchers also learned the bit flip attacks aren't just a hardware issue. They can also seriously threaten the neural network tool. So back in the 2017, the first work showed that fault injection, that also the bit flip attacks could disrupt the neural network model's behavior. And then in 2019 the author found that the attacker can only just flip 13 bits and then turn the ResNet 18 into a totally random output generator. So later the studies went even further, and the author also shown that the attacker can only just flip only one single bit, and that is enough to make the model behave field on some specific symbols while the acting normals on other symbols. And now such attacks has even reached to the large language models and treating the large language models themselves as a victim model. So actually in a neural network, such attack can take effect both the computation period and also the attack the parameters. So, but in this work, we currently focus on the parameters level, which means we assume the attackers can only flip the model's parameters. Actually, this is a reason because we assume the model is already have been deployed on the devices, and the attacker try to bit flip the model offline. Okay. So here we give a very illustrative example. We assume there is a parameter deployed on the memory. So here we give a value from the integer domain. So before we assume the parameters are stored in 8-bit wise. And so before the attack is 85, but assume the attacker flip the signal bit, and then it will change to a very different negative number. And maybe such attack will influence the neural network's behavior. Okay, so after introducing the question overview, now so I'd love to introduce some notations before we define our verification problem formally. So first is, we called in this work is MN attack. Here MN give us some limitation on the attacker's ability. So M limits the maximum number of the attackers can attack the parameters. And the N here denotes the maximum number that for each parameter the attacker can flip the bitwise. So recall back the 1-bit attack here just match to the 1-1 attack. Here both M and N are equal to 1. Okay, so here I give the verification problem we got interested in this work. So given such a tag type definition and given a neural network, a quantized neural network, and given a precondition on the input space and post condition of the output space, we want to try to verify if for any potential attack on the neural networks, after the attack, the neural network also obeys such precondition and post condition properties. Yeah, so for very extreme cases, assume we have only one sample in the input space, then such verification problem is more like the check the accuracy, clear accuracy after the attack. But if we consider some input space, such like example after give some perturbation, then this problem would be, will the attack influence the robustness property of the neural network? Okay, so here I give our overall framework. So our tool totally consists of 2 components. The first is we try to use some sound technique that reachability analysis, and then if the reachability analysis cannot prove the absence of such attack, we then reduce the problem, the whole verification problem, into a MIL problem. That is a mixed integer linear programming problem. So here, so as we can see, they totally contain 2 different components. So the challenge here also come from the 2 components. The first is how can we make a sound and relatively efficient reachability analysis of such attack setting. And the second challenge is we all know the MIL encoding is very complicated and very computation comprehensive, especially for such bit-flip attack settings. So we want to efficiently encode such attack phenomenon and maintain the exactly precious behavior of quantized neural network. Okay, so for the first challenge that we want to design a relatively efficient but also maintain some precision reachability analysis under such attack settings. So for the first step, we try to, I forgot to mention a key point here. For this work, we first try to traverse each parameter first, and then we focus on each potential parameters that can be attacked, because for each parameter there will be some combinational bit attack mode. Okay, so for the first time we compute for each potentially attacked parameters, we first compute the value range of such attack parameters. Assume, for example, we consider for each parameter we can flip only 1 bit, then we try to compute such a width value range for these attacked parameters, what the largest value and the smallest value that the parameter can achieve. So we first compute such a value range and we treat it as a symbolic value, and then we split the neuron associated with a parameter, and we introduce a weighted ReLU function. So such structure change still remain the function semantics. And then we can just make some abstractions on both the weighted ReLU function and the normal ReLU functions. Here, the abstraction means we want to turn such nonlinear activation functions into some linear functions, because we like linear functions because it can help us to make the propagation much more efficiently. Okay, so due to the time limits, I just omit the details and only provide an intuitive overview of what the abstract transformer for the weighted ReLU looks like. So the key idea is we abstract the such nonlinear function into two linear functions. So one is represent the upper bound and the other one represent the lower bound. And then we can just propagate this boundary function in a sound manner, layer by layer. And also in this work, we also investigate the corresponding transformers for other types of activation functions. Okay, so the next challenge is about how to efficiently encoding this verification problem into a MU problem. So for the encoding the precondition and postcondition, this is already existing in previous work, so I just skip here. And for the neural networks under the bit attacks, so we cannot just enumerate all the possible conditions of parameters, but we can use some intermediate results from the reachability analysis phase. So we can first obtain all vulnerable parameters from the reachability analysis. I will show in the later evaluation result, we can see there are a lot of, almost 99% of parameters have been filtered out as a benign parameters by the reachability analysis, and then we can just focus on the potentially vulnerable parameters using such MILP method, complete method. And for each potentially can be attacked parameters, we use such a constraint set to encode the attack behavior. So I just skip here. If you're interested, we can discuss later. And finally, we just can combine all of the constraint and encode the normal network's behavior layer by layer into a single MIL problem. Okay, so for the benchmark, currently we focus on MNIST and ArcSU. ArcSU is a benchmark for the aircraft controller, and here we use some properties that can be proved by the reachability analysis. And here comes the verification result. Here, because this task don't have a baseline method, so we use a very naive method, which means we use a brute force manner to traverse all the possible bit attack and use some traditional neural network verification method to do such things, and we compare the verification results during the reachability analysis phase. So for the yellow part means we obtain some effective maintenance, and the green part means the inherent limitation of such reachability analysis method. And for the red part means the effective loss, because we sacrifice some precision, but we want to get more efficiency gain. So, and the purple part represent the effectiveness gain, also the precision gain. So the conclusion of these results demonstrate that our reachability analysis method is relatively accurate in approximating the bit flip operations. And also we compare the computation overhead. So I say just right now, the reachability of this method is trying to make it more efficient during the reachability analysis phase. And also here I show a complete results that first reachability analysis and then the MILP encoding, and These results show the accuracy benchmark. So the results show this tool can indeed verify the absence of such attack, and either approve it is attacker freeness or return a real attack. Okay, so this is our contribution. So any questions?
Okay, thank you. Let's thank the speaker. And any question?
You mean trying to fix the vulnerability? Yeah, because currently this work is only focused on to detect the vulnerability, but I did remember there's some work trying to make some detection mechanism on the vulnerable parameters, but their work trying to protect all the parameters. So I think maybe this work for the reachability part, they can help to fill out most of the parameter to be protected and then to reduce the overhead, protection of the overhead. Sorry?
It's evaluation, characterization to protect a robust.
You mean the evaluation of?
You characterize, if there is a product that protect the leg of the bit, you can characterize it. You can say that it's more robust than other approaches. It's just characterization, right?
Yes. Yes, we can compare the ratio of the vulnerabilities. Yeah.
Thank you.
Thank you for your question.
Yeah, okay, then that's the end of this session. Let's thank the speaker again. Enjoy it.
Hello, welcome to the verification 3 session. Note for the speakers, what we will do is I'll give you a little 2-minute thing towards the end. At 13 minutes, you have 15-minute slot. We are running a tight ship. And I request when the speaker finishes, I request the next speaker to come set up so that we keep on going. The other thing that I wanted to mention. Yeah, okay, so that should be it. Let's get started with the first talk of the session. We have Awaljot Singh, who is giving a talk on automated verification of soundness of DNN certifiers. Take it away.
Good afternoon, everyone. Good afternoon, everyone. I'm going to talk about the automated verification of the soundness of DNN certifiers. In other words, we are trying to ask the question, can you verify the verifiers? This work is done in collaboration with Yasmin, Charit, and Gagandeep at UIUC. So we have seen in the past that AI is unreliable. There have been several instances of car crashes with self-driving cars, and a lot of the AI models are embarrassingly non-robust to even small perturbations. To deploy these models to safety-critical domains, we need better guarantees. Currently, most of the guarantees are based on metrics like accuracy, precision, recall, but they are not enough to build trust in neural networks. For example, it's easy to fool a neural network to misclassify this as a speed limit sign instead of a stop sign. They involve a set of images or a set of inputs, which are usually infinite. Several ways have been developed to gain reliability in neural networks. The first one, on one extreme, is a testing technique where you sample a bunch of inputs from the input region, and you test the outputs against the property. Now, this is scalable, but this is unsound technique. On the other end of the extreme, we have solvers like SMT solvers or MILF solvers. Now, these are sound. In several cases, they are also complete, but they do not scale. In the middle, we have abstract interpretation-based certifiers. These are sound. They are mostly not complete, but they offer a knob where you can vary the precision and scalability trade-offs. So they offer the perfect solution for neural network verification, and this is also the topic for our research. Abstract interpretation-based certifiers are based on the key idea of over-approximation. So let's say you want to certify the property on a set of images, which is represented by phi here. Now, we abstract out that using some abstraction function, which is alpha of phi, and it is represented using the blue region, which is the over-approximation of the actual set. Now, instead of propagating the actual images through the neural network, this blue over-approximation is propagated through the neural network. But the key thing is that at every layer, at every step, it must be an over-approximation. So finally, at the final layer, we get an over-approximated output. Now, if this output satisfies the property, then we can say the original images also satisfy the property. Now, this over-approximation is important to ensure the soundness of the certifiers. But other things that the developer needs to care about is the precision and the scalability. If it is too precise, it may not be scalable. If it is very scalable, it may not be too precise. So they need to maintain the balance. So everything is so good so far. But the problem really starts when you have to develop one, actually, because the development process is very tedious. It usually starts with an application. The first step is to come up with a mathematical design of the certifier. This involves coming up with an abstract domain, abstract element, abstract transformers, maintaining their soundness, maintaining their precision and scalability. The second step is going and writing long pen and paper proofs which prove that every transformer is an over-approximation of the actual concrete operation. And the third step is the implementation. Now, those in the audience who actually do neural network verification, they will realize this pain, that coming up with the design of a neural network verifier and actually implementing them are two completely different ballgames. Because the granularity at which they are designed is at the neuron in a neural network, that what each neuron is supposed to do. But when they're implemented, neural networks are layers, so they have to be implemented on tensor level. So it's a completely different thing. We provide an alternate approach, where instead of coming up with pen and paper designs, they write in a DSL, which we call constraint flow, because it's basically the constraints which are flowing to the neural network. Once we have a specification in constraint flow, we can automatically verify the correctness of this specification. From correctness, I mean the over-approximation-based soundness. Now, you no longer need to write the pen and paper proof. That can be done automatically. And once that is done, we have a compiler which can compile those specifications into an actual executable that run on neural networks. Now, be it CPU backend or a GPU backend, you will get it for free. Constraint flow DSL was introduced at last SAS in 2024, and this work is presenting proof sound, which is OOPSLA 2025. Let's look at some example certifiers before we go on. The first one, very commonly used, it is the interval bound propagation. It associates two bounds with each neuron in the neural network. So a neural network, I'm considering a graph where the vertices are called as the neurons. So with each neuron, IBP associates two bounds, a lower bound and an upper bound. And the constraint is L is less than equal to N is less than equal to U. We have another very popularly used certifier, which is deep poly. Instead of two bounds, it associates four things. Small l, small u, same as the previous one. But a capital L, capital U, which are the lower and upper polyhedral bounds this time. And the constraints are similar. L is less than equal to N, less than equal to U. Now, these fields that are associated with the neurons are what we refer to as the abstract shapes. And the abstract element is the conjunction of the abstract shapes of all the neurons in the neural network. That's one abstract element. And the constraints, they define the over-approximation-based soundness. So this is the constraint that they want to maintain at each layer. So that is the over-approximation-based property, which I'll refer to as P in the next slides. Now, in constraint flow, these algorithms can be written in just tens of lines of code, as opposed to 10,000s of lines of code in their standard implementation. How? They just need to first write the abstract domain, which I just showed you what it is, along with the over-approximation-based soundness property. Notice the polyhedral expressions. So these are very commonly used in neural networks. They are amongst others. So we provide them as first-class citizens so that users don't have to write much. The second, they define some user-defined functions which help them write the abstract transformer. They are declarative, loop-free, pointer-free, so everything is good for verification. And finally, they write the abstract transformers corresponding to all the operations in the neural network. Affine here represents a fully connected layer and a convolution layer, but users have to write it for ReLU, sigmoid, or whatever activations there are in the neural network. That's all. What do we mean by the soundness of the certifier? Let's assume there is a concrete domain and an abstract domain. Abstract element has been defined, let's assume. And let's say we are given an abstract element A. We also know that this abstract element over-approximates a concrete element C. Now we apply a concrete function to the concrete element and an abstract transformer to the abstract element. What we want to ensure is that the abstract element still over-approximates the concrete element even after the application of the function. But we want to ensure this for all possible abstract elements and concrete elements. Now, notice this for all quantification. This for all quantification induces a for all quantification over all the neural networks. Why? Because A is a conjunction of abstract shapes of all the neurons in the neural network. Now, if we want to verify the soundness of a certifier, we want it to be agnostic of the DNN. DNN is an input to a DNN certifier. But I don't have a way to represent all possible DNNs. Think about Z3. Is there a way to write all possible DNNs? There's not a direct way. So that is the key challenge that we try to address. Now, before going on to the solution, let's take a concrete example. I've slightly modified the deep poly algorithm to show the intricacies of the solution. Let's take the ReLU activation. So from current, I mean a neuron in the current layer. Previous is a neuron in the previous layer. So current is equal to the ReLU of previous. Treat them both as neurons, not as layers. Usually, ReLU is specified in three cases. The first one, when both the bounds of previous are in the positive region. Second, when they're positive and negative. And the third, when both are negative. Let's take the first case. In the first case, ReLU almost behaves like an identity function. So the lower bound, upper bound, lower polyhedral bound, all can be set to the corresponding bounds of the previous. But for the upper bound, we made a slight change. We did previous u dot map replace upper. Let's look at what exactly this is doing. Let's say E is a polyhedral expression, 5n1 plus 6n2 minus n3. Polyhedral expression is simple affine function over the neurons. And replace upper is a function that takes in a coefficient, which is a real number, and a neuron. And based on the sign of the coefficient, it either outputs n of u or n of l, upper bound or the lower bound. Basic idea is we want to get an upper bound based on the sign, upper bound of c into n. So this map construct now applies this function f to all the sum ends of e. So basically e dot map, it's very similar to MapReduce. So it gives us f of 5, n1 plus f of 6, n2 minus f of 1, n3. So similarly, we apply e.map replace upper, we get this expression. The basic idea is we want some upper bound of e. OK, so keep this running example in mind. Now to do formal verification, we first come up with the formal semantics of constraint flow. Now we come up with the operational semantics where the input to the DNN certifier, again, please remember, is a DNN. But when we want to verify the correctness of a verifier, we don't want it to be restricted to one DNN. It has to be correct for all DNNs. So there has to be some notion of a symbolic DNN. And once you have a symbolic DNN into picture, the operational semantics no more apply. So we come up with symbolic semantics, where you have a symbolic DNN, apply the symbolic semantics, and now you can do some verification. Let's look at the concrete solution. The first step is to create a symbolic DNN, which starts with just 2 neurons, which are previous and current. Both of them will be associated with their own abstract shapes, which are L, U, capital L, capital U. Now we initialize all of these entities with symbolic variables, 1 per each. But now if you notice, we initialize this U with a single symbolic variable. How do we apply map? So we need some expanded form of this U. So we do the symbolic DNN expansion, where we replace this one symbolic variable with a full polyhedral symbolic variable. But in order to do so, notice that we introduced 2 more neurons. So we need to introduce that in the symbolic DNN. And they will also be associated with their own abstract shapes. So now this is the full expansion in order to symbolically execute the given expression. Once we have the fully expanded symbolic DNN, now we have the given conditions that the property was already true for previous N1 and N2. And what we want to verify is that the property still holds on current after the application of the transformer. We also assume that current is ReLU of previous. And this can be offloaded to an SMT solver. Coming back to the formalism, now how do we prove that this is whatever we are doing is correct? So we come up with the notion of symbolic semantics over approximating operational semantics, and a symbolic DNN over approximating several concrete DNNs. Now this notion gives us the result that if you prove the correctness on a symbolic DNN, this automatically implies the correctness on all concrete DNNs. But take into consideration the bounded verification. I've not introduced, but there are bounds. And this is 80-page long appendix. For evaluation, we took several certifiers and their corresponding abstract transformers. Most of the verification can be done within 1 to 2 seconds. And we also introduced new abstract transformers and certifiers. So this also shows the utility of constraint flow, that it's easy to develop new certifiers and verify them. To conclude, the whole objective of this work is to reduce the manual effort and increase automation as much as possible. We want to democratize neural network verification and make it available to more and more users. So we introduced a constraint flow spec where you can just write the certifiers in a few lines of code. Proof sound takes it, checks it for over approximation based soundness. If not, you need to come up with a better specification. If it does, it passes on to the compiler, which gives us the final executable. It also allows several future directions. The first one, our current support for the compiler, which we have not discussed yet, but is only for the CPU. We want to extend it to a GPU backend. 2, very interesting, that now since we have all the basic recipes, we also want to extend it to language model certifications and check if that is possible or not. Third, what if we include all of this verification process within the training of neural networks? So this is called certified training, and we also want to support it through constraint flow. Finally, what we are exploring is certifier synthesis. We have all the basic recipes if you see. We have a DSL, we have a checker, we have a compiler. So why not automatically synthesize the transformers for a particular application? So that's also what we are exploring. And there are other future directions possible. I'm happy to take questions now.
We have time for one question, just one.
Toolchain the certifier to real DNNs?
We have applied it to
and what's the performance behaviors?
We have applied it to the standard benchmarks. It works very well. So it will show up in the upcoming paper for the compiler. But the current version is only testing the correctness of a certifier. It is not applying it.
But the certifier yourself, have you applied the certifier yourself?
Yes, it works well.
To benchmarks.
Yes.
Okay, thank you.
Let's thank the speaker again. So our next speaker is Nicholas Lyuchenko. Nicholas is going to talk about bolt-on strong consistency. Take it away, Nicholas.
Okay, can you hear me okay? Okay. Yeah, so this is joint work with Gautam Kaki, my advisor, and Evan Chang at CU Boulder. So if you've been, if you've been at the conference all week, you've probably heard one or more people shout that distributed systems are hard, and it is absolutely true. The more specific claim that safety verification for distributed systems is hard is also true. So why is this? Well, a big part of the problem is that verification in the distributed context takes a bird's eye view. We're looking at global states of the entire network. That means arrays of node states, sets of messages in flight. And that means that we end up with big inductive invariants that have to discuss all those states, relate every message in flight with some state that it came from. It means that it's hard to automate. We have things like arrays, which are not great for decidable fragments. And it's all kind of frustrating because most of this is a model. It's not really the actual code of the system. It's the sort of model of the network, which isn't really the part that's unique to you. The specific code is way down at the worm level, running on a single node, processing a single node state and a single message at a time. So what can we do about this? Well, in this talk, I'll tell you about how for consensus algorithms, we can actually do verification at the worm level. So from the worm's eye view, we can verify by implementing the consensus algorithm using causal replication, by specifying it, the consensus safety property, which is a global property, using the local properties of monotonicity of individual node states and commutativity of messages, and by verifying this using a inductive verification artifact called a stable update precondition. So this is basically the outline of the talk, and then I'll talk about our case study, where we've applied this to a real useful consensus protocol that works like Raft. So yeah, what is a consensus protocol? You might be asking. Here's an example, the party planning protocol. So the point of this protocol is to determine a location for a party. So at the beginning, nodes have no idea where the party will be. Eventually, they learn a location. And what we're trying to avoid is having nodes learn conflicting locations. At that point, safety is violated. You split the party. You might have people show up at different houses, and that's no fun. So the way that this works is nodes sort of run a little election where they pick a unique leader. And so every time one votes, it's broadcasting that message. We're in the causal replicated paradigm here. Once a node has seen that it has received a majority of votes, then it's the leader, and it can pick a party location and broadcast that to the other members. Now, this is causal replication, so that means messages are delivered in like a causal order. So green here, for example, can't learn about the party location until it's seen the vote from purple that enabled blue to actually make the decision. That'll become important in a minute. OK, so how do we verify this then? We can think of our basic inductive verification step is going to look at some event on a node that's starting in a state, processing some code, and ending in a state. And of course, the problem, as I talked about with the bird's eye view, is that the safety of that final state kind of depends on the other states of the other nodes. And even worse, when this event is probably the delivery of a message, an update, and we're going to run some code on it. But where did that update come from? That's going to depend whether it's actually possible to receive it in this state. And even worse, we have an asynchronous system. So really, the update's coming from some kind of like in-flight message queue, and now that's part of the state. And so our safety is going to have to discuss like those messages as well. So again, it's going to get big, and we want to avoid this. So the first way, thing we're going to handle here is safety. We don't want this global notion of safety. So let's think about a slightly weaker property than consensus safety. This is convergence, a property that's going to be familiar to anyone who's worked with CRDTs. The idea is that eventually all the nodes, under some conditions, can arrive at the same state. In this case, they'll know the same location or no location. Okay. So this is not our consensus property. It does allow, in the meantime, nodes to have different locations. And as we saw, if that ever happens, then you could end up with different people at different houses. And so we need to avoid that. So convergence is not enough on its own, but it becomes enough if we add monotonicity. So here, once a node learns a location, it cannot unlearn it. So this is just a relation on individual node states. And once we add this in, we can see that if we have these different node states, or these different locations A and B, that eventually transition to the same location C, if they're following the monotonicity order, that's not possible, and so they would actually have to be the same. So we can get consensus from monotonicity and convergence, and again, for the CRDT folks, convergence we can get from commutativity on pairs of messages. So we have two local properties, monotonicity on pairs of node states and commutativity on pairs of messages. Okay, this is great, but we still need to deal with this, where do the messages come from, what kind of context do we have for those? So the way we're going to deal with that is with a verification artifact called the stable update precondition. So this is just a precondition on updates. So if a node generates an update, its local state has to have satisfied the precondition. So for the announcement that the party will be at 44th Street, the precondition would be that blue has to have recorded a quorum of votes for itself, and its own location has to be none. It can't have picked a location yet, otherwise that would violate the monotonicity that we just talked about. So great, that makes sense. Now we extend this to the notion, the stronger notion of a stable update precondition by saying that it's stable if it's also true for every node state that this update gets delivered into. So purple here would also need to know that quorum of votes for blue, and also its own location would be none. So we're going to inductively verify these, and the base case is pretty simple. It's just whatever code is running on blue that's generating this announcement had better satisfy these properties. But the inductive case, what does that look like? So we could think of this as, suppose there's a message, an update, that is in flight and it's ready to be delivered into state S. So S must satisfy its precondition, that's our inductive hypothesis. But now interference occurs. Another update gets applied to S. So we actually have to show that if S satisfied the precondition of the blue's update, then this new state will have to as well. But we can depend on the fact that for purple's update to have been applied to S, S also had to satisfy its precondition. So if purple's update was a conflicting announcement, that means that S would have to contain a majority of votes for both blue and purple, which can't happen. So we don't have to show that blue's update would still need to hold in that case. That's not possible. Okay, so that's basically how we're going to get this stability. And that will help us obviously with monotonicity, because we just consider that any state that an update applies to has to satisfy the precondition, and then we can get monotonicity. Commutativity is a little different. So we care about commutativity when there are two concurrent messages. So that means that they're both in flight, they're both headed for the same state, they're essentially racing towards that state, and we don't know which one's going to apply first. So in this case, we need to show that it doesn't matter which order they apply in. But just like with our previous verification condition, we can depend on the fact that the state that they're both about to be delivered into has to satisfy both of their preconditions. So again, if we're talking about two conflicting announcements, it can't actually satisfy both of their preconditions, and so we don't have to consider those to be commutative. So this is called racing state commutativity in the sense that it only matters for states in which two updates are racing towards. Okay, so to finish up, I'll talk a bit about our sort of case study of scaling this up to a real consensus protocol. Raft-like in the sense that it has the same interface and safety guarantee as Raft. So this is called Fairy, kind of a pun on Raft. Interesting sort of implementation details. It maintains these trees of logs instead of single logs, which allows you to avoid retransmission. Talk to me later if you're curious about the details. But it's implemented in Haskell on top of a causal replication layer, as I've described. Verification for it was able to fit into extended EPR, so all the verification conditions are decidable, and those the verification artifacts, like the stable update preconditions, size up to about 110 lines of code. An interesting bit on the causal replication is that it simplifies the design of Fairy compared to Raft. So in Raft, there's this important detail that when a follower votes for a leader, the leader has to find out about all of the followers, all the log entries that the follower has seen before it can actually become the leader. And in Fairy, the causal delivery just does this for us. And so we don't actually need to specify this in the code of Fairy. So we did a performance comparison to sort of the leading industrial implementation of Raft etcd to see if this causal delivery thing is going to slow us down. So this is etcd in blue, and this is Fairy in green. So we actually outperformed it on a cluster of 5 machines. And I think there's a couple possible reasons for that. Again, if you're curious, talk to me. But the important thing here is that the causal broadcast did not slow us down. Okay, so basically, just very high-level picture here. We're stacking strong replication, a consensus algorithm, Fairy, on top of causal replication, hence bolting it on. This is not really something that's been done before. In the past, these have been kind of seen as and implemented as sort of separate domains. So that's kind of interesting. In conclusion, I've talked about a new style of verification for consensus algorithms, which is enabled by our discovery of the derivation of consensus from monotonicity and commutativity. It's enabled by our new inductive verification artifact, stable update precondition, and it works in practice for a Raft-like algorithm. So that is my talk. Thank you for attending. Ask me questions.
Please come up to the mic if you want to ask questions. And may I ask the next speaker to come set up? Yeah.
Hello. Thanks so much for the interesting talk. So I was thinking about 2 properties of consensus. One is no duplication, and the other one is termination. So
Okay.
no duplication, if you keep receiving things as you go, then you're receiving multiple times. And then also for termination, if everyone votes for himself, there will not be a leader to broadcast to everyone.
Right, yeah.
So I was wondering what these 2, but again, thanks so much for the talk.
Yeah. So the no duplication, we assume that is part of the causal message delivery system. So that's part of the message layer. The termination, we're not verifying termination, but so the toy sort of example I showed you does not necessarily terminate. There might be a tie, and then the party never happens. But for Fairy, like Raft, we get this sort of probabilistic termination where new elections can start after random timeouts, and so eventually, in practice, we will have termination. Thanks.
A quick question. Oops. Yes. Quick question. This is pen and paper verification of the Fairy protocol, right?
So
have you, or are you thinking of
okay, so I mean the soundness of the sort of inductive verification technique with the strong update preconditions is pen and paper. Given that, then the verification of Fairy is automated using an SMT solver. So, yeah. Thank you.
Let's thank the speaker again. So the next talk will be given by Gaurav Thakkar on memory safety verification of open programs with angelic assumptions.
So I would like to I would like to start with a question that this program strncpy, which copies n strings from source to destination, does it violate memory safety properties? So, like as we can see here, it will violate this property at multiple locations. So, it will give us errors at line 4, line 6 and line 8. And for each of these cases, suppose if the SRC is pointing to a string which does not contain null character, then also it will give error at line 4. And if the size of the destination is smaller than the size of the string which SRC is pointing at, and it is also less than n, then also it will give an error at line 6 and line 8. But when these functions are called in complete programs, we assume that SRC, whenever these functions are called, SRC is always pointing to a null terminated string, and the size of the destination is of length n. But when we give this function to a verifier, it will have demonic behavior. It will assume that the inputs can take any value. So, in that case, it will give you it will give us these these errors at multiple locations. So, these kind of programs where we don't have any information about the environment, these are called open programs. And these inherent assumptions about these functions, whenever we are calling, we call them angelic assumptions. But since the verifier doesn't have these assumptions, it will give us many false positives. So, it decreases the confidence of the tester or programmer, and they are not able to like trust whether the error that verifier has given, it is actually correct or not, right? These are false positives. So, they tend to ignore them. So, my talk is on automating generation of these angelic assumptions for these open programs and verifying them for memory safety properties. This work was done in conjunction with Baldeep from IIT Kanpur, Prantik, who is working at MathWorks, Akash from MSR India, and my supervisor Subhajit Roy from IIT Kanpur. So, formally what we want is that given a program P and some user given assumptions about this program, we have to synthesize an angelic assumption set psi such that when we verify it for memory safety properties, we are able to suppress most of these false positives. But if there are any true positive, we do not want to suppress them. So, we divide our approach into two parts. One is that we try to find out some patterns about these angelic assumptions which we make, and these templates are done like using LLM to find out the idiomatic patterns which are commonly used in these programs. And the second part is that using this template to actually synthesize the angelic assumptions. So, first part is how do we come up, how do we use LLM to find out these idiomatic patterns of for memory safety programs. So, first we ask the LLM to generate more than like in our case, we ask LLM to generate more than 1900 programs which does these buffer manipulations. For each of these functions, then we collect what are the inherent assumptions for these functions. We generalize these assumptions, and from these assumptions we extract what are the idiomatic patterns which are being used here, and we shortlist them based on like what are the more frequent more frequent patterns, and these patterns are then given to the verifiers, experts. Then they can see that whether these assumptions patterns make sense or not. So, from these templates, from these patterns, we come up with these 7 assumption templates. So, first is the null terminated string. So, suppose if P is a pointer, then there is at least one memory location where a null character is stored in this, right. So, for example is that strlen and strncpy. So, these kind of functions assume that this str or src, they point to null terminated strings. Another is the non-overlapping buffers. So if there are multiple arguments, multiple pointers, then we don't want that the buffers they are pointing to, they should not overlap with each other. And similarly, there were other templates which we found out, which we used in our experiments. Okay, so now we have got these templates. The next step is, can we use these templates to synthesize the angelic assumptions? So let us take the same example and go over like how do we generate these assumptions. For, this str and CPY is the same function. First, we instrument it for memory safety properties, and the instrumented code is then given to the verifier, which gives an error trace. So here in this case, it found out okay, there is an error at line 4, and this error trace is then given to this weakest liberal precondition synthesizer. So this this gives us a weakest precondition such that this error should be suppressed now. Now, using this weakest precondition, we try to come up with a angelic assumption based on those templates, such that whenever that angelic assumption is true, this weakest liberal precondition will also be satisfied. If we are able to synthesize, so which is the case here, we get that SRC should be a null terminated string. In that case, we again go to the verifier and we again try to verify with this assumption. So in the next iteration, it comes up with another error. So it finds out that okay, even if we give this assumption, there is an error at line 5. So for this again, we go through the same process. We again generate the weakest precondition, and again we are able to synthesize that if the size of the destination is equal to n, then it will always suppress this error, right? Then again we go to the verifier, but now there are no more errors. So it returns as okay, this is a false positive. It will give us a list of all the errors that it encountered, and it will classify them as false positives with the assumptions that were used to suppress them. But if we are not able to synthesize any these assumptions in any case, then we identify them, okay, these are the true positives, so these are the actual errors, and they are given to the user. Okay. So we evaluate our work on like 182 open benchmarks taken from VeriSec benchmark suite, which is commonly used for memory safety verification. Here we classify these into two categories. One is the safe open programs, where if there is no true positive error, so all errors should be suppressed in this case, and unsafe programs where at least there is one error trace that should not be suppressed. That is an actual error. Okay. When we evaluated, we found out that no unsafe program was declared as safe, meaning there were no true negatives, with, true positives which were classified as false positives. And we were able to suppress more than 75% of the false positives. We also compared with the existing tools like Angelic AV, where like AV is designed for bugs like divide by 0 or null pointer. So, but it is not designed for memory safety properties. So, we can see it in the results also. So, for the unsafe benchmark, it shows that total number of the red part is the total number of counterexamples encountered, and the blue part is the number of counterexamples suppressed by these tools. So, here we can see that in case of unsafe benchmark, both of them perform similarly, and they are not suppressing most of the bugs. But in case of safe benchmarks, where most of them are false positives, we can see that Seeker is able to suppress most of these bugs. But AV is not able to do that. Okay, thank you. Any questions?
We have time for questions. If you have questions, please walk up to the mic and ask the questions. So one question I had is, can you handle dynamic memory allocation, malloc and free? If I have two buffers that are newly allocated, can you synthesize, can your system?
Yes, yes. We can handle that.
Okay. So what about programs? So you're assuming your notion of true and false positives, right? They are based on the angelic invariance that you infer, right?
Yeah, angelic assumptions. Yeah.
So how do you know that they are correct?
So our angelic assumptions are based on like what is commonly used, like what is in practice, right? What the programmers use. So these idiomatic patterns are we give them to the verifier also as a warning that okay, if some counter error trace was there, so we will also give okay, this assumption was used to suppress this. Then the user can see whether it is reasonable or not.
Okay. Yeah. So these are very standard. These are the assumptions that other systems also make.
Yes.
Okay. Any other questions from the room? If not, let's thank the speaker again. Thank you. Yeah, let's, you can get set up. Okay, so let's welcome our next speaker, Sarzor Shadai. She will talk about mini-batch robustness verification of deep neural networks. Yeah, take it away.
Thank you. Hello, everyone. My name is Sar, and I'm excited to present my paper, Mini-Batch Robustness Verification of Deep Neural Networks. This work was conducted jointly with my advisor, Dana Drexler-Cohen at the Technion. So let's begin with the motivation. Okay. Neural network image classifiers are widely used across many domains, including safety-critical applications such as autonomous vehicles. Despite their impressive success, they are found to be vulnerable to adversarial attacks, which are small, carefully crafted perturbations added to the image pixels that can cause the network to misclassify, which can be very dangerous. In order to assess the safety of these systems, we use verifiers to formally prove the network's resistance to these attacks using the local robustness property, for example. So given a network, an input image, and a set of all image variants within an epsilon distance around it, a verifier attempts to prove that all inputs in this neighborhood are classified correctly. And there are two categories of verifiers. Sound but incomplete verifiers can determine robustness when it holds, but they cannot always determine a violation. Whereas sound and complete verifiers can also find a counterexample when the robustness doesn't hold. So this local robustness property that I just showed you is with respect to a single input image in a single neighborhood. But in order to estimate the robustness level of a network in general, it is common to determine the local robustness for a set of inputs. Okay, so most verifiers analyze neighborhoods one by one. And for reliable estimation, though, large sets of inputs are necessary. The larger, the better. So this becomes highly inefficient. Okay, so to mitigate this, our approach to expedite the analysis is to, instead of verify neighborhoods one by one, we verify mini batches of neighborhoods through a counterexample guided abstraction refinement procedure, while dynamically learning the optimal batch size. So you see how this is much faster. Okay. So let's dive into the problem definition. A neural network image classifier N takes an input image X and determines which class it belongs to. The input layer of the network consists of the pixels values, which are then propagated through the hidden layers of the network. Each hidden layer consists of neurons, where each neuron applies an affine transformation of its inputs and weights, which is then followed by an activation function. We focus on the common ReLU activation function, the rectified linear unit, which is non-linear, but it consists of two linear parts, the active part and the inactive part. Then at the end, the neuron with the maximum value in the output layer determines the classified class, the predicted class. Okay, so let's define more formally a local robustness. Given an input image x and a small number epsilon, the L infinity epsilon ball around x is the set of all inputs that differ from x by at most epsilon. In practice, this forms an interval for each pixel, represents the range of values it can get. And we say a network N is locally robust in the epsilon ball of x if it classifies all the inputs in this neighborhood the same. There are various techniques to prove local robustness. One example is interval arithmetic, which propagates the bounds of the neurons and determines robustness only if the lower bound of the correct class is strictly larger than the upper bound of all other classes. While this method is okay, it is not complete and it's not precise enough. So instead, we focus on mixed integer linear programming or MILP verification, which is also complete. A well-known example of such a verifier is the MILP verify, a complete verifier that encodes the network computations with linear variables and constraints and sends to an optimization solver to search for a feasible assignment. During this process, for each ReLU neuron that can be both active and inactive, a binary variable is added to capture the two possible states. And therefore, the complexity of MILP verify is exponential in the number of binary variables. And remember, this verifier can only be applied one by one neighborhood at a time. And every neighborhood runtime is exponential, so it's not very efficient. Okay, so these definitions brings me to talk about our problem. In our paper, we address the group local robustness problem. Given a classifier N, a set of inputs S, and a small number epsilon, our goal is to determine whether N is locally robust for every X in its epsilon ball while minimizing the overall analysis time. Okay. So with the exponential runtime, which can make each query highly inefficient, each query to the verifier very inefficient, how can we mitigate this? Okay, so our approach was to, instead of verify neighborhood one by one, we will take an abstraction of multiple neighborhoods and verify them together in a single query. Okay, so the most naive approach to do this is, given a set of inputs, abstract all their epsilon balls. For example, I can take these two epsilon balls and bound them in their convex hull and verify the hull instead of each ball individually. However, because of the over-approximation error, this can lead to spurious counterexamples which invalidate the verification. So a more promising idea is to abstract the epsilon balls of similar inputs. For example, in this subset of cars in CIFAR 10 datasets, I've noticed 4 images that highly resemble each other. Naturally, their epsilon balls are close and may even overlap, making their convex hull much more precise. However, when we tried this approach, we still noticed many spurious counterexamples, along with a very long overhead because of this neighborhood growth. Okay. So our first insight is, what if instead of abstracting in the input layer, we will abstract the neighborhoods in an intermediate layer? Intuitively, this makes sense because neighborhoods tend to shrink in deeper layers because each layer compresses the information while extracting features relevant for classification. So it can make the neighborhood in the intermediate layer more precise. Our second insight is that we cannot simply abstract all inputs in the set because it might lose too much precision. So instead, we divide the set into mini batches, which are small subsets of inputs for which the network performs similar computations, for which we believe the intermediate layer neighborhoods will be close. Okay? So this approach brings two main challenges. The first one is how do we know which inputs to put in a mini batch together, and what should be the mini batch size, how many inputs to include. And second, how can we perform an efficient refinement when we fail to prove a mini batch? When we find a counterexample, how do we know whether it is spurious? And if not, how do we know which epsilon ball is non-robust? Okay, so regarding the mini batch size, we applied a multi-armed bandit or a MAB agent, which is an algorithm from reinforcement learning adapted to our settings. So here, instead of arms, we had batch sizes, and each reward is the batch velocity, which is the rate in which the analysis progresses. And this is eventually what we want to maximize because we want to terminate faster, the verification. And in each iteration, when we want to prove a new batch, the MAB agent recommends a batch size. We then construct the batch, verify it, and observe its velocity. And then the MAB agent updates the batch's distribution, which allows him to learn on the fly the optimal mini batch size and exploit it for later iterations. Now, given a batch size, how do we choose which inputs to include? So remember, we want to group inputs that are close in intermediate layers. So in order to approximate similarity in intermediate layers, we used activation patterns. An activation pattern is a binary vector for every input, whose ith entry is 1 if the ith neuron is active in terms of the ReLU state, and 0 if it is inactive. And for every pair of inputs, we compute the Hamming distance of their activation patterns. So now we have distances between inputs. Okay, so to allow dynamic extraction of clusters at varying sizes, we use those distances to apply hierarchical clustering. This dendrogram is the result of this algorithm. And then we represent it as a binary tree of inputs with batch size in the inner nodes. And this way, if we need a batch of size 2, we can simply extract, for example, this batch. But while if we need a batch of size 4, we can take a larger subtree. Okay, so finally, when we find a counterexample, how do we determine whether it is spurious? And if not, which epsilon ball is non-robust? So the answer to this question relies on the way we abstract the neighborhoods. Because with convex L abstractions, we observed that most counterexamples do not actually belong to any of the original epsilon balls, making them uninformative. So instead, we encode the union of the neighborhoods, which restricts the counterexample to fall in exactly one of the neighborhoods. Okay, so these are the key ideas behind our algorithm, Beverly, a complete batch verifier for local robustness. Given a network, a set of inputs, their class, and a small number epsilon, so Beverly constructs efficient batches. It computes their bounds in an intermediate layers, unify them, verify them, and applies refinement when necessary. It learns dynamically the optimal batch size with the MAB agent, and at the end it reports for every input in S whether its epsilon ball is robust or not. Now let's turn to the results. In our first experiment, we evaluated Beverly on sets of 100 inputs and compared it against the MIP verify, the one-by-one naive verifier. I will walk you through this table one step at a time. So we evaluated two data sets, MNIST and CIFAR10, on two types of networks, convolutional networks and fully connected networks of varying sizes. We considered the first 4 classes of the data sets and the epsilon values shown here. And we report the verification time in hours, as well as the speed up factor. So as you can see, on average, Beverly achieved 2.3 speed up with a maximum speed up of 4.1, reducing the analysis time from 24 hours to only 6 hours. In our second experiment, we evaluated 3 networks across a dataset of 2 different classes. We evaluated the average verification runtime per neighborhood with respect to the input set size. And these results show a clear trend. The larger the dataset, the faster each neighborhood is verified, which demonstrates the effectiveness of both our clustering and similarity, because intuitively larger datasets provide more similar inputs to group and enable the agent, the MAB agent, more opportunities to learn and exploit the optimal batch size. And you are welcome to check out our paper for additional results. So to conclude, I presented Beverly, a sound and complete verifier for group local robustness. Beverly analyzes mini batches of epsilon balls with similar network computations and scales the one-by-one verification. And I also invite you to check out our GitHub. And that's it. Thank you for listening.
We have time for questions. So I'll start with a question. So so I noticed that the network sizes are up to few hundreds of neurons. Is that
few thousand?
Few thousands
the
of.
larger one is 7,000 neurons.
7,000 neurons. Do you? I also assume that you're running these on CPUs, not GPUs, right?
Yeah, because Gorobi optimization is it runs faster on CPU.
Okay. Do you have insights on how to take this to GPUs so that we can sort of scale this, or is that not because typically the actual networks are much larger, right? So and I see that it's a couple of hours. Even though you have a 4x improvement, we still have like large ways to go, right? Do you have? I mean, is there fundamentally something that restricts your methods to not be applicable on a GPU?
I think maybe with MILP encoding, it's a bit a challenge. But if you try, we already tried to apply this method on state-of-the-art verifiers such as Alpha Beta Crown, which works also on GPU. And it's still work in progress, but I think that in the future we will be able to group inputs and terminate faster the verification, but on more scalable verifiers. Yeah.
There is a question.
Yeah, thanks for the great talk. And I'm wondering that whether we can apply this technique to the any architectures like transformer or CNN kind of things.
CNN, we showed it works on, but transformers, that's a good question because it's a different architecture. We haven't tried, but maybe we can talk about it later. If you like.
Yeah. Thank you.
May I ask the next speaker to get set up while you are answering the next question?
All right, thanks for a nice talk. So one aspect of efficiency is the batching. That's very cool. I wonder if you've seen observations or have thoughts of whether there's opportunity for reuse across batches in some way in the verification.
To reuse what?
To have some sort of reuse of the verifications across the different batches, if there's an opportunity for that to incrementalize.
You mean a patch adversarial attack?
Right, across the batches, yes.
Yeah, I believe it can be used in other attacks as well. We haven't tried it, but let's talk about it. I will be happy to.
Let's thank the speaker again. be Zhu, who would be presenting scalable equivalence checking and verification of shallow quantum circuits. Yeah, take it away.
Sorry, like this one? Yeah, okay. So, yes, I am Zhu and come from Stony Brook University. And today I'm happy to present our work with the title Scalable Equivalent Checking of and Verification of Shallow Circuits. And this is my joint work with Nan Kunju from Stony Brook and Thomas Rapp from University of Wisconsin. And before we go into the concrete problems, I would like to start with some news. Recently, a scientist working on quantum hardware was awarded the Nobel Prize in Physics. This recognition highlights the growth of global attention and investment in quantum technologies, both from academia and industry. It reminds us that quantum computing is no longer a theoretical but an engineering and verification challenge that we need to solve today. Let's see the motivation of our work. Equivalent checking of quantum circuit is a fundamental verification task. And to translate our computation model to a quantum circuit that can run on a real hardware, we need compilers. So equivalent checking ensures that compiler optimization preserves the correctness of the programs. And why should we take care about shallow circuits? Shallow circuits are the class of circuits with constant depth, and they are particularly important in the near-term era because of some reasons. First, they require only short coherence time, which makes them suitable for near-term hardware. And remarkably, they already demonstrated quantum supremacy in Google's experiments in 2019, meaning that they can outperform classical machines in certain tasks. And a simple example of a shallow circuit with 8 qubits at depth 3 is here. Each layer applies 2 qubit gates on a pair of qubits with time progress from left to right. The gates are unitary operations, and quantum state of the system is represented by a vector. This gives us a concrete structure in 1D to keep in mind, but we can also consider circuits with more complicated structure in 2D, 3D, etc. And the most direct way to check equivalence between two circuits is to simulate them classically and compare the outputs. Given a circuit C and an input state psi in, we apply the circuit to get the input, the output. Sorry. And there are 2 simulation types. The first one, strong simulation, where we compute the exact output probability for every output string. In weak simulation, we sample bit string from the output distribution to mimic the behavior of quantum devices. Unfortunately, both methods require exponential resources in number of qubits. And so while simulation is intuitive, it does not scale. Additionally, some worse news come from complexity theory. DiVincenzo showed that if shallow circuit can be simulated efficiently, then the complexity class BQP is a subset of the class AM, a classical class. And then it means no quantum advantage against classical machines. Then after that, G and Wu proved that approximate equivalent checking for shallow circuit is QMA hard. We remark that BQP and QMA are the analogs of the class P and NP in classical complexity. Then these results suggest that simulation is unlikely to be the path to efficient verifications. And up to this point, it's still unclear whether efficient equivalent checking is doable. And in fact, conventional wisdom would say no. First, equivalent checking is another form of verification. And most verification methods rely on exploring the state space to check some key properties of the output. But exploring the state space of a quantum circuit somehow means simulating its behavior. So if equivalent checkings were easy, then simulation should be also easy, but it's not. And surprisingly, we discover a method which is scalable and classical, which avoid exponential simulation entirely, and we call it projection-based representations. Here's a quick preview of our results. This plot compares the runtime of equivalence tracking for circuit update 3 using traditional state vector simulation versus our method. The red and green curves show the runtime of the state vector simulation method. They exponentially blow up when the number of qubits increases. However, the orange and blue curves show our method's runtime that scale linearly with the number of qubits. And this computational advantage allows us to scale verification to larger circuits. And let's formalize the problems. We consider two variants. The first one, fixed input equivalence. The question here is whether two circuits produce the same output on the on-zero input state. And the more general versions, arbitrary input equivalence checking with the questions whether two circuits produce the same output for every input state. And we restrict ourselves to consider constant depth circuits with arbitrary gate set, and each gate only acts on a constant number of qubits. Let's see our key idea. Instead of storing the output state as a vector explicitly, we represent it using a tuple of local projector, projection matrices, P1, P2 to Pm, and each projector acts on a small set of local qubits, which is determined by forward light cones, a concept that we will revisit very soon. Then the output psi R will be the unique common eigenvectors of these projection matrices. Okay, here's an example for the forward light cone of qubit Q3 and Q4 in the qubit in the circuit that we see earlier. The gates in the light cone are blue, and the side of the light cone is bound by the constant depth and independent of the number of qubits. Local position will be computed inside this light cone, and the number of light cones is linear in the number of qubits. Let's see how it works. Our algorithms begins by initializing local position. For example, here, for qubit Q3 and Q4, we start from projector corresponding to vector 0, 0. Then we update the projector layer by layer using Heisenberg picture for evolution of quantum operator, where U is the unitary operator acting on the projector support. Finally, the intersection of these local position images fully characterize the output state. We apply that representation to check equivalence between two circuits C1 and C2 for fixed input or 0. The problem will be reduced to checking whether the circuit C1 dagger C2 performs an identity operation on the on-zero state. And we know that C1 dagger is the inverse of C1 because it is a unitary operation. And we compute the local position of this combined circuit and check if the on-zero vector is in the conjunction of the images. In summary, we transform equivalence checking into checking a set of local constraints. And for arbitrary input equivalence checking, we apply choice isomorphism to reduce the problem to a fixed input equivalent checking with a larger circuit. And the processes avoid full state simulation entirely. We also analyze the complexity of the method. The runtime T and D is linear in the number of qubit n for fixed depth, and the exponential blow-up only depends on the depth T of the circuit and the geometry of the circuit. And here we show runtime for computing local position for random circuit in 1D at depth 6 with the blue curves. The red curves present the runtime for state vector simulation, which quickly becomes infeasible. And in contrast, our method scale linearly and run comfortably up to 200 qubits on our device. We compare our equivalence checking with classical state vector simulation method on the same machine. And on the left is the runtime for checking depth 3 circuit. We already seen it earlier. On the right is the result for depth 4 equivalence checking. State vector simulation seem faster at small size circuit, but this is only because we stop it early. Each runtime will explode right after that, or in some case, or in many cases, the memory will be insufficient to run simulation. And this highlights the clear advantage of our approach for larger system. Yeah, and this is the scaling for runtime in the problem of arbitrary input equivalence checking. It is still linear in number of qubits. Before the conclusions, we highlight the two applications of our method. The first one is an efficient classical description for shallow quantum circuit outputs. Then in the paper, we also design a class of assertion languages to verify compiler translation and operation on quantum devices. Then let's wrap up. Shallow circuits are important, but traditionally hard to verify. And we introduce a precision-based method for exact equivalence checking that scale linearly in number of qubits at fixed depth. And this enable practical verification and runtime assertion checking on real devices. Yeah, thank you for listening, and I'm open for your questions. Thanks.
We have time for questions. Yeah, please walk up to the mic if you want to ask.
Very nice. I have a question. So already for depth 4, things become much harder.
Yeah.
I want to know how many gates do you have in there when you have n qubits and say depth 4? How many gates are we talking about in the circuit at that point?
Yeah. Let me.
So in particular, can you do up to like close to 4 to the n or 2 to the n?
Yeah. The circuit that we run these experiments on, they are of the same structure here, with the same structure and up to 200 qubits for each circuit at depth 4, and each gets random unitary matrices. Yes.
So one question I had is, it seems like the method that you presented works very well at 3, and at 4 state vector performs very well. I mean, at least for the experiment that you had shown, right?
Yeah.
There's an explosion. Is there, is there opportunity for thinking about a combination of these that might work for better depths? I'm curious why, when you mentioned shallow, it was like 3 and 4 seem like both seem shallow.
Yes. Yeah, 3 and 4. In fact, we have a method to classically simulate quantum circuit efficiently in depth 1 and depth 2 already. And depth 3, we just present just very first experiments in depth 4 and depth 3. Just they are still very first result, and we will continue the works.
Excellent. Yeah, thank you.
Thank you.
Let's thank the speaker again.
Thank you.
verification session 4. And yeah, now we start. So we will talk from, the first talk will be some of the products of the recursive programs for hyper safety verification by the Rotung Chang from University of Toronto.
Thanks for the introduction. Let's look at this recursive program that computes integer division. Stating and proving its partial correctness require nonlinear integer arithmetic. Alternatively, we can state properties that relate multiple executions of div, such as scaling. When n at least doubles, div at least doubles. It is an instance of hyper-safety properties. Specifically, a k-safety property is a property whose violation is witnessed by k finite length program runs. Hyper-safety is k-safety where the arity k is greater than 1. The expectation is that we can prove hyper-safety properties without having to prove partial correctness first. It's well known that hyper-safety verification can be reduced to one safety verification by constructing a product program. Self-composition is the first product construction proposed. For k-safety, it makes k disjoint copies of the input program, p1 to pk, and concatenates them. For iterative programs, the problem of product constructions is somewhat well studied, and there have been many of them. The question we ask in the paper is, what are product programs for hyper-safety of recursive programs? To answer this, we first need to understand why we need more than one product construction. Let's recall the scaling property. We make two copies P1, P2. With self-composition, proving safety requires guessing an inductive summary of div that must be nonlinear. Consequently, existing provers cannot establish the safety automatically. We can also argue running the two copies in lockstep doesn't really simplify the proof. Conceptually, to avoid nonlinear reasoning, we need a variation of lockstep that matches every two calls of P1 against one call of P2. But what if the constant 2 is changed to 3 or 4? Or even a property that looks more different, such as distributivity? It's intuitively clear that all these need different product constructions. Thus, recursive programs inherit from iterative programs the complication of needing a universe of product programs. In addition, they have a new challenge. For that, let's recall the concept of interprocedurally relatable paths. Such paths of P1 are illustrated here and can be produced by a context-free grammar. We use round brackets to denote calls and returns, and dots for internal actions. By definition, the brackets are balanced. Similar for P2, except that we use square brackets to differentiate from the first copy. Suppose we want to prove the version of scaling with constant 1. Let's interleave in lockstep tau1 from P1 and tau2 from P2, both making two function calls. We can alternate between the statements from the two copies in the naive way, which leads to a mismatching between the types of brackets. This cannot be a run of one recursive program, and we will not be able to leverage existing techniques for safety verification of recursive programs. Formally, the set of all such interleavings is not a context-free language. However, a small twist is sufficient to make this example work. At the returning phase, we may as well start the alternation with P2. Then, this does look like a run of one recursive program. And we have a generalizable proof in linear integer arithmetic. Let's go back to this picture of using product programs for hyper-safety verification. We have seen that when the input program is a recursive program, the construction should be expressive, closed under the class of recursive programs, sound, and efficient. Since soundness is so critical, we look at it first. Given a run, swapping adjacent letters from disjoint copies do not affect the overall semantics. We may repeat this operation any finite number of times, which still preserves the overall semantics. Then, all possible interleavings are divided into equivalence classes according to whether they can be rewritten to the same run. Note that we identify PI with its realizable path. The shuffle operator here is just the shuffle of languages. For a set L of interleavings, a reduction of L is defined as a subset that contains one representative from each commutativity equivalence class. We have that any reduction of the shuffle is safe if and only if the input program is hypersafe. Therefore, to guarantee soundness, we can construct reductions as product programs. But how do we select one reduction, such as lockstep, out of the infinitely many? For that, we introduce a scheduler, which conveys the user's idea of the reduction. As expected, the maximal product can be the shuffle. The scheduler then guides the construction of the reduction of the shuffle. It does so by giving the preference for the next statement based on the partial run so far, which is mathematically a function from partial runs to total order on the statements. We call it a contextual order, and the reduction induced is a contextual X reduction. Schedulers formalized as contextual orders lead to this picture, but it's problematic in two ways. A general contextual order is not really describable, and the output doesn't satisfy the closure property that we mentioned. To solve these problems, it's first important to understand when can a reduction be viewed as a classical recursive program. Intuitively, it means two things. The reduction should be finitely representable, and each run should be able to be simulated on a single stack. This needs to be made formal. The representation should be able to express the realizable path. For better theoretical properties, we use visibly pushed-down automata and grammars. The languages they induce, VPLs, form a subclass of context-free languages. Moreover, we require each run to be well-nested, which I will explain. A run row in the shuffle is called well-nested if any matching call and returning row belongs to the same PI. For example, these are ill-nested, whereas these are well-nested. But why is well-nestedness sufficient? This is because a well-nested product program can be reinterpreted as a classical recursive program in a formal sense. By default, the product operates on a k-tuple of stacks, but we can also view it as operating on a stack of k-tuples. We can prove for all well-nested partial runs, this shift of semantics doesn't affect the validity of any Hoare triple. With a little effort, one can find a set of conditions on the contextual order to make everything work out theoretically. However, in addition to the natural requirement that the order is VP representable, there is an extra condition, which we call coherency, which places extra burden on the user to check. Thus, we consider an alternative path. We define a new shuffle operator, the well-nested shuffle, as the shuffle restricted to well-nested runs. The good thing is, reductions of the well-nested shuffle are by definition well-nested. Note that the well-nested shuffle is not closed under commutativity. The constructions in the literature do not reduce a non-closed language for technical reasons, but in this case, we managed to put this out. And the result is, if the contextual order is VP, this reduction is also VP. The proof goes by linking to the coherency condition and using this very nice property that VPLs are closed under well-nested shuffle. Thus, we go from this picture to this. But can we go further? It would be great if the user doesn't need to specify their reduction idea at all. That is, the algorithm searches for a reduction and the proof at once. But that turns out to be not scalable, especially for recursive programs. So instead of eliminating this description completely, we try to allow a simpler description, trading expressivity for user friendliness. Let's revisit the properties we've seen so far for the div example. We can identify some basic building blocks. Scaling uses a variation of log step, where the first copy runs s times as fast as the second copy, depending on the constant s. As for distributivity, we can write the reduction as the composition of two reductions, O plus and O times. Intuitively, O plus should be a sort of concatenation, but this is different from self-composition. We should nest the second copy fully inside the first copy, and lockstep the result of this with the third copy. We call the new concatenation operator nested concatenation. These building blocks are all formalized in our paper. Then we introduce canonical reductions as all combinations of the building blocks. The key result is that applying any building block to the wall nested shuffle gives a contextual lex reduction induced by a VP order. So canonical reductions can be connected to the lex reductions that we have defined. We implement our method as a tool called hierarch. Let's look at some of these components. When the reduction idea is given as a canonical reduction, it looks like this expression for solving distributivity. The tool also accepts contextual orders, but we don't expect them to be the common usage. We have 3 construction algorithms whose details can be found in the paper. To verify the one safety, the tool outputs CHC encodings of the automaton or grammar. Both are linear in size of the object. For the experiment, we use 3 different CHC solvers and take the best. We have 103 benchmarks in total, each labeled with a canonical reduction. 45% of the benchmarks were acquired from the literature, including those that search for reductions. We have 3 baselines: sequential composition and 2 versions of direct encodings without reductions. The line illustrated here is the best of the 3 baselines. The arithmetic benchmarks solved by the baselines are exactly those with a function summary in linear integer arithmetic. The 2 constructions that produce grammars show significant improvements over the number of benchmarks solved. Perhaps a little surprising, the construction that produces automata is slower, but is better at solving challenging benchmarks. Hierarch is the best of the 3. The paper contains a detailed analysis of the 5 benchmarks that fail. In the end, I'd like to share a few things that we learned from doing this work. First, our reductions are syntactic in nature, but syntactic reductions can be powerful as well. There is an example in our paper whose iterative version was cited in a previous paper as a challenging example that requires data-dependent alignments, but our method can do it easily, which is because we operate on expressive and unbounded syntax instead of manipulating the code. However, there do exist examples that truly require data-dependent alignments, and it would be interesting to investigate those. Last, canonical reductions, as well as their iterative analog, are useful. They may offer a practical solution to program alignments that sits between one fixed reduction, which has limited expressivity, and fully automated alignment search, which has limited scalability or requires user-provided abstraction in practice. Thanks. This is the end of my talk, and I can take questions.
Okay, questions?
Okay, thank you for a good talk. I have 2 questions. The first is, when you require some user input as a spec, are you trying to using something like program synthesis to get a spec that can prove your goal? The second thing is, I want to make a confirm. When you are changing the push down system into the VP, are you seeking the decidability? Thank you.
Okay, so for the first question, we're not using program synthesis because the user encodes their reduction idea as a contextual order or a canonical reduction. But it may be interesting to investigate if it's possible to synthesize a scheduler. And I think I didn't fully understand the second question. Could you elaborate on that?
Okay. So you said that for some reason you didn't use the purely push-down system, but you used something called VP.
Yes.
I guess are you seeking? The reason why you do that is you are seeking the decidability from the system. Is that right?
Yes, and also VPLs are closed under intersections and complements, and all kind of things makes the construction easier.
Okay, thank you so much.
Thank you.
Okay, thank you. And we will start with the second talk. The second talk is the embedding quantum program verification into Daphne, and by the Henry Allard from the Iowa State University. Yeah.
Thank you for the introduction. Good afternoon, esteemed faculty and staff, faculty and students of OOPSLA 2025. I'm Henry Allard. I will be presenting our work on embedding quantum program verification into Daphne. This is a joint work combined with Feifei Zhang, Sushan Vanjapuram, Saeed Jafari, Alex Potanyan, and Li Li. So how many here are familiar with quantum computing? Okay, I'm seeing some hands. That's good, that's good. Some of this will be review, unfortunately, but why quantum computing and why verification? You've probably seen in the news plenty of articles ranging from informative to sensationalist, but quantum computing is focused in the industry because of its impact, or its potential impact for substantially faster algorithms. They'll unlock orders of magnitude and speedups for complex problems such as cryptography, gene folding, and data processing. Some of these example algorithms include Shor's algorithm, which is for factoring large numbers in polynomial time. This is maybe the most famous quantum algorithm. Grover's algorithm that deals with unstructured search in a sublinear time, O of square root of n. There are also algorithms for simulating physical systems and solving linear equations. But how are these algorithms constructed? Currently, we use the gate model of qubits and circuits to construct quantum gates. So a single qubit can have infinite states, and qubits can also become entangled. This is where a lot of the complexity arises when dealing with quantum systems. So constructing algorithms with qubits in entanglement and qubits in multiple states can be very difficult, time-consuming, error-prone. Most of this work is done by physicists and doctorates. A question of our team was, how can we make this easy for regular computer programmers? So writing out the state semantics of each qubit is difficult. How can we reasonably encapsulate this in a program semantics? Not everyone has a quantum computer, so how can we allow developers to write code and verify that the results are correct on their own physical classical computers? And also, how can we design this language to develop more use cases for quantum algorithms? Our answer to that was QAFNI and QAFNI-C. Previously, we introduced QAFNI, which was a theoretical language for quantum computation. However, now we've implemented QAFNI in QAFNI-C. This is a proof system capable of automatically verifying quantum programs, and it compiles directly down to Daphne. QAFNI-C is based on Hoare logic, so terms like pre and post condition, loop invariance, and the QAFNI triple should be familiar here. And we can use SQIR to compile QAFNI down to OpenQ assembly. So before we talk about exactly what QAFNI is, I'm going to do a little rundown of quantum computing. In the classical world, we have a bit, which is a 0 or a 1. However, in the quantum world, we can have more of a gradient between the two. To notate this, we use vector notation, alpha and beta. Alpha and beta are both probability amplitudes. Alpha squared is the probability that the qubit will measure 0. Beta squared is the probability that the qubit measures a 1. Likewise, the sum of the squares must equal 1. We can extend that by saying vector 1, 0, therefore 0. We call this ket 0. Vector 0, 1 is 1. We call this ket 1. But then we can get more complicated, longer qubit strings. Vector 0, 1, 0, 0 would be a classical 0, 1 or a ket 0, 1. However, in quantum, I mentioned entanglement before. We can combine these kets with amplitudes to create new states. For example, the ket plus, which is the probability of measuring a 0 or a 1. We can also prepare these states in entanglement. This is an example of a Bell state preparation, where we apply Hadamard on the first qubit, controlled NOT gate onto the second, the final product of which is 0, 0 or 1, 1, not 0, 1, not 1, 0. If we measure a 0 from the first qubit, a 0 must result in the second. If we measure a 1 from the first qubit, a 1 must result in the second. So what have we introduced in QuAFNI-C? In QuAFNI-C, we have a new automated verification system. We can use types to direct our analysis and verification, and we've introduced 2 new types, or we've modified the EN type and introduced the amplitude amplification, or AA type. We've also extended the condition semantics to cover a greater range of programs and algorithms. This includes adding 37 verified quantum programs and some critical developer features, such as debugging support and feedback when Daphne fails. So as an example of QuAFNI code, this is a very simple example of the Bell pair state. We have an 11-line method here. We have a precondition requiring that the input to the program is ket 0, or is 2 ket 0. We have a Hadamard gate application, then a controlled NOT, working from the first qubit onto the second, flipping the bit, and then finally ensuring the precondition is 0, 0, or 1, 1, equally likely. This is the Daphne code. It compiles down to, I don't expect you to memorize all of this, it's almost 220 lines. So as our design for QuAFNI-C, we've abstracted quantum circuits into C-like programs. This is evidence very similar to Daphne code. We can also verify pre- and post-conditions of the quantum circuits, and we can simplify the specification of quantum semantics. And finally, we automatically verify those QuAFNI programs in Daphne. So what does automated verification look like? So QuAFNI-C will automatically convert QuAFNI code in Daphne, adding the required pre- and post-conditions based off of the shorter semantics we use in QuAFNI programs. For example, to specify, again, that Bell state, we can use this very simple line of QuAFNI code, an entangled type, 2 possibilities, both amplitudes 1 over square root 2, 0, 0, or 1, 1. This QuAFNI-C will take this and then convert it into a few lines of Daphne, here checking the amplitudes and the basic kets at the end of the program, at program end. And what does type-guided automation mean? In QuAFNI, in the second paper, we've introduced AA types and EN types with a parameter. We can generate constraints based off these types, and the type complexity drives Daphne code complexity. So we have 4 quantum types, NOR, HAD, AA, or amplitude amplification, and EN with an N parameter. The NOR type represents any basic ket, 0, ket 1, ket 1, 0, 1, 1, 1. It's represented in Daphne with real and a sequence of bit vector 1s. This is simpler compared to the other types. Hadamard type represents any singularly superpositioned qubit, so ket plus, or maybe 2 ket pluses. Amplitude, it is converted to the Daphne type of amplitude real and a sequence of reals. Amplitude amplification is used for a specific group of problems that I will get into later. All that you need to know now is that it basically partitions the qubit string into 2 separate groups. This can be represented as 2 sequences of length 2, a sequence of reals, and a sequence of bit vector 1s. And then finally, EN type. This can represent any qubit string. An example value is this GHZ state. Essentially think Bell pair, but for more qubits. The n decides the number of sequences, so it's an n-dimensional sequence of reals for the amplitude and an n plus one dimensional sequence of bit vector 1s for the basic kets. What is amplitude amplification? An easy example of this is Grover's, where we're splitting basic kets into a good and a bad group. Essentially, amplitude amplification problems work by increasing the probability of measuring from the good group and decreasing the probability of measuring from the bad group over time. This requires constant or multiple applications of the quantum circuit. An example of what the semantics look like, this comes directly from the original paper, Amplitude Amplification and Counting. This is what amplitude amplification problems essentially look like in practice. This graphic shows kind of how successive rotations around a state vector collapse the state closer to the target vector. So to help with these problems, we've introduced the amplitude amplification type. It separates the 2 groups with different amplitudes by a function that returns true for the good group, false for the bad. This is a very simple example from the Grovers. We can see we're partitioning the basic kets into ones where the geometric sum of the amplitudes is sine v when f returns true, and where the geometric sum of the amplitudes is cosine v when f returns false. So in QuaffneyC, we also have over 37 verified programs, including Grover's, Shore's, Simon's, and amplitude estimation. As an example of how complex these programs get in Daphne, Belpaire, again, turns into 220 lines. Grover's, which is 23 Quaffney lines, turns into 230 Daphne lines. We've also introduced some useful features, such as two-line feedback, converting the Daphne error codes into Quaffney ones. This is really useful for larger files, such as amplitude estimation, which has over 100 lines. So we can convert directly from Daphne back into Quaffney. Our findings are that Quaffney can quickly verify algorithms with fewer lines of code and better feedback to the programmer. We have these are the 37 programs that I've been mentioning throughout this talk. As we can see, they're ranging to maybe a maximum of 50 lines of code, whereas compared to CoQ, QBreaks, and SQIR, even something like GHZ can get to 119 lines of code. So it's a lot easier to write code or write quantum programs and then verify them using Quaffney. In the future, we hope to use symbolic execution to generate pre and post conditions, add additional features, additional language, semantics, and cover a wider variety of programs, and then use this in some real-world research papers, maybe create some new algorithms, and publish the Quaffney code associated. Thank you very much for listening. I now welcome any questions with the remainder of my time.
Do you have any questions?
Hi. So you're mentioning you're verifying Grover's algorithm. I have two questions. So for one, you have this target oracle that you're optimizing for in the Grover iteration, right? This function that you want to satisfy. What function are you using for that? And did you notice that, like, when you use more complex target functions, that like the solvers struggle, or does it actually scale?
That's a great question. Essentially, we accept in a function, like I believe it's a natural that returns a Boolean, and we can base it off of that. We don't, in the actual proof, we don't define that function. So we leave it up for Daphne to figure that out. So I hope that answers the second question as well. We don't make it complicated, so it doesn't. We can't really compare different functions. But thank you for the questions.
Hi, thank you for the nice talk. So from the kind of small snippet that I was able to memorize of the slide that you flashed,
oh no,
I saw that there's like a lot of quantifiers and complex features and so on.
Yes.
Did you struggle with Daphne performance, or did you employ some tricks to get it to go through the proof?
Yes, actually, our paper mentions more on that, but a key insight was using sequences that are immutable in Daphne over, I believe, arrays, just because it was faster. So some of the longer ones did take like up to a minute. Some of them took a while to massage into verification.
Okay.
Hope that answers your question. Thank you.
Yeah, thanks. Yeah, a minute is nice.
Very nice talk. Could you say a bit more about what is the property you verify for Shor's algorithm?
For Shor's algorithm. The end state of the qubits. I'm not sure I understand the question. I'm sorry.
So it's very complicated to state the correctness property for Shor's algorithm because the algorithm is probabilistic.
Yeah.
So I'm wondering what your correctness statement is.
I'll take a look at that and I'll get back to you. Thank you.
Okay, so we Okay, we can start. So the last talk is the interactive bit vector reasoning using verified bit clustering by the Henrik Wöving from the Lean Focused Research Organization.
Thanks. Hi everyone, I'm Henrik Wöving. I work for the Lean FRO and as a master's student at LMU, and I'm going to present joint work with the University of Cambridge, Stanford, CMU, and ENS Lyon on interactive bit vector reasoning. So first of all, why do we care about this? Well, historically, bit vectors are a highly successful domain in automated reasoning. When people want to verify low-level programs in C or in assembly or do hardware verification, they often reach either directly for SMT solvers that are capable of bit vector reasoning or for higher level tools like model checkers that then reduce to these bit vector logics under the hood. However, these highly automated tools often suffer from proof instability issues where when you do slight refactorings to your code or things like that, heuristics might be misguided and then suddenly proofs get slower, start timing out, etc. So for this reason, we advocate for people to use interactive theorem provers such as Lean to give the users more control over their proof scripts so they are more stable under changes. However, we sometimes still encounter combinatorial problems where it's just too annoying to do interactive verification. So for example, here we have two implementations of a random number generator, and the second one is doing some micro-architectural tricks to get some speed-ups, and we might want to verify that these two are the same for security reasons. But I mean, we could try to think about why exactly the modulo operation is equivalent to this fancy stuff, or we could just ask an SMT solver and it's going to say, yes, they are equivalent in a second, and then we are happy. And this is exactly the kind of capability that our work brings to the Lean ITP with a new tactic called BBDecide. And BBDecide basically takes an arbitrary goal in Lean about fixed width bit vectors, and then it applies a pipeline very similar to the current top solver in this area called OOPSLA, where first we run a normal proof by contradiction, and then a large set of rewrite rules, approximately 200 ones, on our new goal state to simplify it, and these rules are really important to get good performance in practice. Then we reduce the conjunction of all of our assumptions into a circuit called end-inverter graphs, reduce that to a CNF, and then hand this off to a SAT solver. And the SAT solver can then do two things. It can either say, okay, there's a model for your assumptions, in which case we cannot derive a contradiction and we can recover a counterexample back to the user, or it can say there is no model, and then this is where we leave the BitWutzler part. It can also provide us a proof that there is no model, and then we can replay this proof into Lean to convince Lean that indeed there is no model, so there must be a contradiction here. As we are working in Lean, all of the steps that are marked in blue in this diagram need to have a correctness proof on their own. Unfortunately, I don't have time to go about the design of all of these components, so I'm going to focus on the first two, as I think those are the most interesting for other work. To verify all of these rewrite rules, we need to do a lot of arbitrary with bit vector reasoning, because of course we want to apply them in any kind of situation. So the first thing we did is do a lot of bit vector library engineering. And we did this using a similar approach to other components in the Lean standard library, where we first write out all operations that we care about. So in our case, every operation from SMT-lib's bit vector logic plus a few additional custom ones. And then we think about what ways are there to extract information from the results of these operations. So for example, we could try to interpret the result of an addition as a NUT, as an int, or think of it as a bit vector, so an array of booleans in LSB or MSB order. And for each of these interactions, we have a theorem that describes what happens, plus more creative theorems, such as algebraic properties, properties relating the different operations to each other, and so on. So we now have this very complete standard library for bit vectors in Lean that we then used to verify all of these hundreds of rewrites rules that we got from BitWutzler. And of course, also the reduction to circuits. But to reduce to circuits, we need a definition of circuits in Lean. And in particular, as we are executing this definition with potentially hundreds of thousands of nodes, it also needs to be quite fast. And the circuits we're using are so-called AND inverter graphs, which is a very simple model where basically you have inputs, and then all of the logic gates are AND gates, and then depending on the color here, there either is an inverter on the fan-in or to the AND gate, or there isn't. And the way we encode these circuits is we have this Deckel data type, which can be a constant, an input, or a gate. And unlike you might expect, the Deckel gate does not recursively contain other declarations. And this is because we need to do sub-circuit sharing to avoid exponential overhead. So instead, the natural numbers here are indices into this array of declarations that the AIG is carrying around with itself. So we basically have a memory arena, and these left and right natural numbers are pointers into this arena, if you wish. So for example, here the third gate says my left input is the thing at index 0, and then that's this guy. In addition, when we're building up the circuit, we also need to be able to tell when there is a shared subcircuit somewhere. So that's what this cache is for, and this cache is built on top of the hash map from the standard library, which already has previously a similarly complete API, so we can just reuse that component without doing any theory on our own. And notably, both the array and the hash map have the same asymptotics as they would in C++ because of Lean's functional but-in-place optimization. So array behaves like a std vector, basically. And then on top of this definition, we build a framework for reasoning about functions that build up these AIGs, which unfortunately I don't have enough time to go into, and then also the remainder of the pipeline with the CNF reduction and the LRAD proof checking. Now, as all SMT solvers, which we basically are now, we care a lot about performance. So we did an evaluation on 2 data sets. The first one we mined from LVM's inst combine pass, which is about 8,000 problems, and then compared BBD sites performance against the previously mentioned top solver written in C++, BitWutzler. And as we can see, we barely have any performance difference here, apart from a few problems towards the end, which is an encouraging first result. So then we went further and took all 46,000 problems of bit vector logic in SMTlib, and we compared it on BBD side as well. And we took in a third tool called CoqQFPV. CoqQFPV is also a verified SMT solver, but it has no ability to interact with Coq. So it's written in Rock and Isabelle, and then extracted out into OCaml, and it runs as a separate binary. It's no tactic or anything like that. It's a normal SMT solver, if you wish. And we managed to outperform CoqQFPV by a few thousand problems. But unfortunately, unlike the previous graph, there's quite a bit of gap between BBD site and BitWutzler here. And the main reason for this gap is that in SMTlib, there's a lot of problems generated from model checkers that just translate a large C program over into bit vector logic. And the bottleneck in BBD site then is the rewriting. So once we are past rewriting, everything is as fast as we could hope for. But for rewriting, we're currently using the built-in simplifier in Lean, which has a lot of additional features like unification, higher order rewriting, and so on, which can't keep up with BitWutzler's specialized rewriter at the moment, basically. So we eventually plan to close this gap by implementing a more specialized rewriter. And as a last step on top of all this, we implemented a deeper integration with Lean's type system, where, as a little example here, we have an elevator state machine which has a current floor it's on, and a low and high floor that it may go to, and then a direction it's currently stepping towards. And these floors are also not directly encoded as bit vectors. They are wrappers around bit vectors, UN16s. And then we have the step function, which bounces the elevator back and forth between the lowest and the highest floor, step by step, basically. And here we're doing a lot of things that are not directly bit vector related. So we branch over this enum with pattern matching, we project values out, update values, we do arithmetic with the UN16s. And then we can prove a very simple invariant about this, which just says we always stay between the low and the high floor by just doing induction over the amount of steps that we take here, and then unfolding the repeat and in function or definition, and running BBD sites. So all of these funky operations here, all of the branching, etc., is happening in the SAT solver. There's no case splitting in Lean, so we basically have support for a simple C-like fragment natively in BVDecide, a simple C-like fragment of Lean. So in summary, Lean now has a high-performance bit blasting tactic, and in addition to that, also a large bit vector theory in its standard library and a performant ARG library in theory that we hope will be useful for all kinds of future work that relates to bit vector theory in Lean. Thanks for your attention.
We have plenty of time for the ask questions, so yeah, please come here to ask questions.
Hey, great talk. I just have a simple question. I just wonder if the BVDecide can support some variable length big vectors. So if it is supporting some kind of concatenation or split operations and correctness for that.
So the length needs to be known. So I mean, you can do concatenation of known length bit vectors without issues. If you want to do arbitrary width reasoning, so with a symbolic width, my collaborators here are the right people to talk to. They are currently working on this. And
glad to hear that.
Yes.
Thank you.
Do you have more questions?
Hi, thanks for your talk. I was wondering, since it's like so close in performance to OOPSLA, could you imagine using this as just a general purpose bit vector library for like just outside of Lean, just for general problems, or is there something about it that makes it better suited for Lean than for just general purpose applications?
I mean, you can do that. The question is whether you want to really. So oftentimes SMT solvers are just used to get such results, of course, and then you don't care if it's verified because you can just check the such result yourself. If you're interested in unsuch results and you want to be really sure that these unsuch results are correct, then BVDecide might be interesting for you as a general purpose SMT solver. And we have that wrapper on GitHub already. We used it to build this evaluation here. Yeah.
Thank you.
It's on OOPSLA is the name. Yeah.
Hi, thanks for the interesting talk. My question is about, so your performance are run on the verified SAT solver, so do you still need to produce some kind of certification for the models?
No, the SAT solver is not modified. So we are using Cadical, and Cadical just has natively the capability to output these proofs. Basically, these error proofs here are just a trace of the CDCL algorithm, and it's just outputting its conflict clauses and how it arrived at these conflict clauses.
So there's no extra overhead for producing?
No, there's actually a paper called Faster LRAT Generation Than Checking from the Cadical people. So producing this LRAT proof is faster than even verifying it's correct. Yeah.
Thank you.
Okay. So this will be the end of this session, and yeah, thanks to the speakers again, and yeah, thanks for coming.